GCE Advanced Level Chemistry Practical Series, experiment number 26. Examination of properties of phenols. In this practical, we aim to observe the acidic nature of phenol and we aim to observe different other reactions revolving around phenol. Now, let's take a look at the introduction. Introduction. Both alcohols and phenols contain an OH group. Both alcohols and phenols contain an OH group. However, the properties of phenols are different from alcohols due to the fact that the OH group of phenols is attached directly to an aromatic ring. Now students, you should understand both alcohols and phenols contain the OH group in it. However, when it comes to phenols, the OH group is directly connected to a benzene ring. This changes the properties of phenols compared to alcohols. Precautions. Concentrated solutions of the compound phenol are quite toxic and can cause severe skin burns. It can cause severe skin burns. Phenol, when it comes into contact with the skin, causes burns. Therefore, it should be handled with care. Now students, when you are handling this particular substance in the lab, you have to take precaution. Otherwise, if it comes into contact with your skin, it will cause a skin burn. Apart from that, phenol is toxic. You should not be ingesting phenol. Now let's move on to the next slide. Why are phenols more acidic compared to alcohols? In aqueous solutions, alcohols dissociate and show the following equilibrium reaction. Now we are going to observe one fact about phenol, that is, phenols are more acidic than alcohols. Now students, this will be a good time to remember how acidic alcohols and phenols are. When it comes to talking about acidity of different organic substances, we immediately think about three acidic substances. One is alcohol, which is having very low acidity. Then we have phenols, which has moderately high acidity compared to alcohols. And then we have carboxylic acids, which are the most acidic compared to the two compounds that we mentioned before. So when it comes to alcohols, alcohols show reaction with metallic sodium. Now to test the acidity of a substance, we can use three main tests. We can react that substance with sodium, we can react it with sodium hydroxide, and finally we can react it with sodium carbonate or sodium bicarbonate. Now the stronger acids will react with all three of these substances: sodium, sodium hydroxide, and sodium bicarbonate or sodium carbonate. However, the weaker the acid, they will only be able to react with either one or two of these substances. So when it comes to alcohols, alcohols show reactions only with sodium out of the three that I just mentioned. When it comes to phenols, phenols react with sodium as well as sodium hydroxide. However, phenols are not acidic enough to show a reaction with sodium carbonate or sodium bicarbonate. But carboxylic acids will easily react with sodium metal, sodium hydroxide, and our sodium carbonate. So keeping that in mind, we can be very clear about the fact that alcohols are not as reactive as phenols. Now we are going to observe why that is. So you can see here, when you are adding an alcohol into water, alcohol and water will have this equilibrium. The O and H bond in the alcohol will dissociate to form an alkoxide anion. So RO minus is referred to as the alkoxide anion, and it will be forming H3O plus. So this indicates that alcohols are capable of acting as acids. However, when it comes to this particular equilibrium, the equilibrium position lies quite a lot towards the left-hand side of this equilibrium. Therefore, the amount of H plus that comes in the medium will be quite low, indicating that this is not a very strong acid. When it comes to phenols, however, it is a little bit different than that. When phenols react with water, it will produce phenoxide anion. What we have here, the formula is the phenoxide anion and H3O plus. When compared to the previous equilibrium position of the second equilibrium lies further towards the right hand side. It lies further towards the right hand side, making it possible for phenol to dissociate more and more into phenoxide anion and H3O plus. Now this is why we say alcohols are not very acidic. As you can see, the equilibrium position of this particular reaction lies more towards the left hand side. When it comes to the second equation, equilibrium position lies more towards the right hand side, producing more and more of these phenoxide anion and H3O plus. So there's few details here that we should pay attention. The RO minus ions are referred to as alkoxide ions, and CH or C6H5O minus are known as phenoxide ions or phenoxide anion. So the formula of the phenoxide anion is given here. You can see this is the structure actually. The structure of the phenoxide anion is given here. Now let's move on to the next slide. Now let's take a look at this slide. Phenols are more acidic compared to alcohols, and we can see when it comes to this particular equilibrium, the equilibrium of alcohols reacting with water lies more towards the left hand side. So the equilibrium position of this particular equilibrium lies more towards the left hand side. Now students, the reason behind this is the alkoxide anion that is formed here is not very stable. The alcohol compared to the alkoxide anion is more stable. Because of that, the reverse reaction is favored, so the equilibrium position shifts to the left hand side more. Because of that, the H plus ion concentration that you're going to see due to this reaction is quite small, making this a very weak acidic substance. So alcohols are not very acidic, and one of the main reasons for that is the alkoxide ion that is formed here is less stable compared to the alcohol. And when you are talking about phenols, reaction between phenol and water, as you observed earlier in this particular slide, reaction between phenol and water is going to be a reaction where you produce phenoxide ion and H3O plus. Over here, students, the phenoxide ion that is formed is more stable compared to phenol. Compared to the phenol that we have here, phenoxide ion is more stable, which will cause the forward reaction to happen more, or forward reaction will be favored, causing the equilibrium position of the equilibrium to shift to the right hand side, producing more and more of the products, which will increase the H plus concentration. Now this is the reason why phenols happen to be more acidic compared to alcohols. Equilibrium position of phenols in this particular reaction lies more towards the right hand side. Main reason for that is alkoxide anion being more stable compared to the phenol. Now, with that information, over here in this slide also they say, we need to have a look at why phenoxide ion is more stable compared to the phenol. So that is what we are going to be observing next. We are going to observe why we consider the phenoxide ion to be more stable than phenol itself. Now let's take a look at the resonance structures of phenol. Now before we start, we say that the alkoxide ion is stabilized. We say alkoxide ions are stabilized with the help of resonance. So we have to take a look at both phenol and phenoxide ion. Now take a look at this particular phenol's resonance structure. As you can see, phenol, when connected to the benzene ring, the lone pair of electrons that are found on oxygen get delocalized into benzene's delocalized electron cloud. So we can say this one of the lone pairs found on oxygen gets incorporated in benzene's delocalized electron cloud. This increases the electron density of benzene and activates the benzene ring. So when it comes to electrophilic substitution reaction, this is a good thing. This will make phenols more reactive towards electrophilic substitution reactions. However, that is not what we are going to be observing. That is not the main point that we are trying to discuss here. So we'll see why phenol is less stable compared to phenoxide ion. One of the reasons why phenols are less stable compared to phenoxide ion through resonance is that when resonance structures like this are formed in phenol, we observe a positively charged ion as well as a negatively charged ion. This is referred to as charge separation in resonance. So this charge separation is not contributing to increasing the stability of this structure. Whenever you have charge separation, that does not contribute to stabilizing the structure. However, if you are observing the phenoxide ion, you would observe that phenoxide ion does not have a charge separation. Right? So that is the reason why phenols are less stable compared to phenoxide ions. Now before we go on to that, I need to show how these resonance structures come into place. So students, when you are drawing resonance structures, keep in mind you need to show that this lone pair of electrons are getting incorporated into the benzene's electron ring or benzene's delocalized electron cloud actually. So this lone pair of electrons are getting incorporated into benzene's delocalized electron cloud, and these resonance structures will be a result of that. So what actually happens here is this lone pair gets donated between oxygen and carbon to form a double bond like we see over here. And as a double bond between oxygen and carbon gets formed, since the carbon present at this location can't have 5 bonds, this double bond breaks and the electrons pertaining to that bond will be donated to the carbon that is pointed to over here. So the electron pair that we see here on the second carbon will be donated between the second and the third carbon to form a double bond. This will cause the double bond between the third and the fourth carbon to break, and those electrons pertaining to that bond will be donated to the fourth carbon that we see over here. So you can see we have now drawn those electrons on the fourth carbon, and when you have a pair of lone pairs on that particular carbon, you can see that that carbon is carrying a negative charge. Over here we can see the negative charge on the second carbon, and this will continue to happen, and this bond will break. The electrons pertaining to that will be donated to the carbon that is next to it, forming a negative charge on the sixth carbon here. Again, when that lone pair is donated here, you will see the oxygen and carbon double bond will break, and the electrons pertaining to that bond will be donated back again to oxygen, again allowing oxygen to have two lone pairs of electrons. Now, this indicates how resonance structures of phenol are made. And one thing to observe here, students, is that when it comes to the very first and the last structure, those are not necessarily the same. You can see the double bonds are not in the same exact locations. So when it comes to Kekule's structure also, we have two resonance structures there. For benzene, you can see these two structures have double bonds in two different locations. Those are also not necessarily the same. So now we know how the resonance structures for phenol are drawn. When it comes to the exam, when you are drawing resonance structures like this, keep in mind you have to make sure you draw the right structures, and you have to make sure if you are drawing curvy arrows to draw the curvy arrows correctly. Curvy arrows should always start from a bond or from a pair of lone pairs, making sure that the arrow head is pointing in the right direction. And the base of the arrow should be connected to where the electrons are. Keeping that in mind, let's move on to the resonance structures of phenoxide and iron. So when it comes to the phenoxide and iron, you can see the lone pairs on oxygen. Out of the lone pairs on oxygen, one lone pair of electrons will be incorporated into the delocalized electron cloud of a benzene ring that they are connected to. And again, just like in phenol, you can see electron density in the benzene ring will go up. Although this is similar to what happens in the phenol, what you don't see here is a charge separation between oxygen and the benzene ring. You don't see a charge separation when it comes to this particular structure, which makes this structure more stable compared to the resonance structures that you see in phenol. And this is why when it comes to the reaction between water and phenol, the equilibrium is shifted more towards the right hand side, producing more and more of the phenoxide and iron. Unlike in phenol, it says, unlike in phenol, the resonance structures of phenoxide ion do not show any charge separation, no charge separation. This increases the stability of the phenoxide ion. We say the phenoxide ion is stabilized by resonance. When considering alkoxide ions, such resonance structures are not observed. So when it comes to the reactions between alcohol and water, we form alkoxide ions. However, alkoxide ions, no alcohols actually show any resonance that stabilizes them further. Because of that, you can say alkoxide ions are not going to be stabilized by resonance, which makes alcohol more stable than the alkoxide ion. Because of that, the reaction between alcohol and water, when they produce alkoxide ion and H3O plus, is going to be having an equilibrium position that lies more towards the left hand side where the alcohols are, and not more towards the right hand side where they produce alkoxide ions and H3O plus more. So that is why alcohols are less acidic compared to phenol. Now everyone, we are moving into the next slide where we talk about different types of tests to identify alcohols and phenols separately. Let's take a look at the first test. Identification of phenols with the use of benzene diazonium chloride. We have prepared benzene diazonium chloride before as well. Benzene diazonium chloride is a diazonium salt which is somewhat unstable. So we have to maintain a low temperature to make sure that it doesn't decompose into forming phenol. So benzene diazonium chloride, when reacted with phenol in alkaline medium at low temperatures, they form an azo dye. And this azo dye is orange in color. Right? The azo dye that is formed is orange in color. This test is specific to phenols. So when you have phenols, we can actually identify the presence of phenols by reacting the phenol with benzene diazonium chloride in the presence of an alkaline medium. But at the same time, we have to make sure when this reaction is taking place that the temperature is kept between 0 and 5 degrees Celsius. This will produce a orange color azo dye when you're reacting a phenol with benzene diazonium chloride, and if you maintain this temperature and if you have alkaline medium, what you produce is an azo dye. A parahydroxyazobenzene is the name of the compound that is formed. However, what we are going to be observing is what is important, which is the formation of a orange color. Do we see the same reaction with alcohols? No, alcohols do not give us the same reaction. Alcohols, when reacted with benzene diazonium chloride, will not give you an azo dye. And therefore, there will be no observation, there will be no color change that is observed here. So because of that, we can use this test to identify the presence of phenol separately from the presence of an alcohol. In this slide, we take a look at how this experiment is usually carried out. We can see we have benzene diazonium chloride here. We can see the benzene diazonium chloride is here, and we have our phenol here. And you can see the hydrogen in phenol or hydrogen in the para position of phenol is going to be going away with the chloride ion attached to benzene diazonium chloride. So these two will be removed as HCl, and the phenol will attach itself to benzene diazonium chloride. This is actually a electrophilic substitution reaction that is taking place, and they form an azo dye which is referred to as parahydroxyazobenzene, which happens to be orange in color. So this reaction can be used, like I mentioned earlier also, to identify the presence of a phenol. So how we do this experiment is shown here. Since we have to maintain a low temperature, we have to do this experiment in an ice bath. We have to conduct this experiment in an ice bath. You will take an ice bath, and first of all, we will cool phenol in alkaline medium. Now students, just a little bit of detail that is important when it comes to reaction like this. Phenol is not soluble in water. However, phenol shows acidic properties. It will react with an alkaline medium. So therefore, phenol will dissolve in an alkaline medium. And that is why we take phenol in alkaline medium, to make sure there's no layer separation, to make sure phenol is dissolved in the aqueous medium here. So we will place this test tube containing phenol in alkaline medium in an ice bath to bring down the temperature, and then we will have in another test tube benzene diazonium salt, and we will allow them to cool down until the temperature of these solutions reach a temperature between 0 to 5 degrees Celsius. After that, we will slowly add the phenol in alkaline medium into benzene diazonium salt while making sure that we mix the solution quite well. You will slowly add the phenol in alkaline medium into benzene diazonium chloride containing test tube, and you will see the formation of an orange color azo dye. So the compound that is formed here is an orange color azo dye, which is para-hydroxy azobenzene. So this is how this experiment can be carried out. Now, let's take a look at the second test. Identification of phenols with the use of bromine. And what is the color of bromine? Especially bromine in aqueous medium appears to be brown in color. So when you are reacting an alcohol along with a bromine, or when you react alcohol and a bromine together, you would not see any significant reaction. You would not see any observation. However, when you react phenol with bromine or bromine water, you would see the color of bromine, which is the brown color of bromine, will get decolorized. The brown color of bromine, you can see, will get decolorized when you react bromine with phenol. When you react bromine with phenol, you can see the brown color will decolorize, and along with that observation, another observation you would make is that a white precipitate will be formed. So this white precipitate is due to formation of 2,4,6 tribromophenol, which the structure of that is given here. Now, if you can remember, students, at the beginning of this theory part, we discussed the fact that when it comes to phenols have this OH group connected to the benzene ring. And we mentioned that the benzene ring is going to get activated when a group like this that has lone pairs are connected to the benzene ring. And you can see here, specifically in the ortho and the para locations, the electron density is elevated or increased a bit more. Now we know when it comes to the electron or lone pair of electrons that are on hydrogen gets incorporated into the benzene ring, we know that benzene ring's electron density goes up. We say that the benzene ring has now been activated, especially for electrophilic substitution reactions. So when it comes to electrons coming into the benzene ring, especially in the ortho and the para locations, the electron density will be increased a bit more. Because of that, you can see that the OH group directs the electrophilic substitutions more towards the ortho and the para locations. And apart from the OH group, if you take a benzene ring, groups such as OH, NH2, they both have these lone pairs of electrons. These lone pairs can get delocalized into the delocalized electron cloud of benzene and show such reactions. Apart from these two groups, OCH groups, OR groups, I will indicate it as OR groups, and NR groups or NHR groups, all of these groups are capable of activating the benzene ring and directing substitution groups more towards ortho and para locations. So when you are adding bromine water to benzene that contains either one of these groups, you can actually see the formation of a white color precipitate along with the decoloration of or decolorization of bromine. So you have to keep in mind that when it comes to this reaction, you have to keep in mind when it comes to this reaction, it's not only phenol that will produce the same results that we see here. If you have aniline or benzene connected to NH2 group will also give us the same result, same observation. The color of the bromine will get decolorized when aniline is reacted with bromine water, and at the same time you will see the formation of a white color precipitate, 2,4,6 tribromoaniline. And an experiment regarding this is also conducted, so please go and watch that video as well. Now when it comes to benzene connected to an OH group, we have the phenol which has activated the benzene ring, especially the electron density in the ortho and the para locations. Ortho and the para locations are increased, directing nucleophile groups to these three locations. And you can see this causes the formation of 2,4,6 tribromophenol, which is a white color precipitate, and due to bromine reacting with phenol, the bromine's brown color. Now brown color of bromine is there due to Br2 molecules being dissolved in water, and as the reaction proceeds, Br2 molecules will no longer be present in the medium, because as they react, bromine atoms will be attached to the phenol molecule. So therefore the brown color that you observe in bromine water will be decolorized. So the observations again are mentioned here. Bromine water is brown in color. As it reacts with phenol, the brown color will disappear and a white color precipitate will be formed. Alcohols, that is very important. Alcohols will not react. Alcohols will not react to give the same observations. So we can use this reaction to separately identify phenols and alcohols. In the third test, we are using neutral ferric chloride, identification of phenols with neutral FeCl3, ferric chloride. Phenols and alcohol separately can be taken into two test tubes, and then these two test tubes can be reacted with FeCl3 or can be added with FeCl3. So we take them into two test tubes, and then into each of these test tubes we will be adding neutral FeCl3. So alcohols and neutral FeCl3 will not give us an observation. You will not necessarily see any noticeable observation. But if you take phenol and if you react it with neutral FeCl3, you will be seeing the formation of a violet color. Now this violet color is a very prominent color that you observe. It is not a very faint formation of a violet color. Violet color that you observe here is going to be quite prominent. You will be very clearly seeing the formation of the violet color. And then if you take this solution which appears violet in color and react it with HCl, you will see, or when you increase the H plus concentration in this violet color solution, you will see the violet color gets decolorized. The violet color will get decolorized. So this test is a special test which we can use to specifically identify the presence of compounds that contain OH groups or COOH groups, but we will be looking into that separately as well. But for this particular part, you have to keep in mind phenols can separately be identified by alcohols with the use of this experiment. Over here, the violet color actually is formed due to the phenoxide anion and Fe3 plus ions forming a complex. That complex is going to be violet in color, and as you add HCl, the phenoxide ion again turns back into phenol, causing the complex to break down, and you will only have Fe3 plus ions in the medium. You will see the complex that we saw here is no longer going to be present there because phenol is reformed again. When you reacted FeCl3 with phenol, you can see phenol will dissociate a little bit into forming phenoxide ions, and phenoxide ion and Fe3 plus ions together will form a violet color complex, but in acidic medium. Phenol will be reformed. Phenoxide ion will convert into phenol. So therefore, you will not see that violet color anymore. Right, everyone. So now we are moving on to the next test. Identification of phenols with litmus paper. Identification of phenols with litmus paper. When blue litmus paper is introduced into a sample of phenol and alcohol separately, only phenol will change. Only phenol will change the color of blue litmus paper to a red color. Alcohols will not change the color of the litmus paper. Now, students, we remember that phenols are acidic. They are acidic enough to react with sodium hydroxide. Alcohols did not show such strong acidity. It was only acidic enough to react with metallic sodium. Alcohols did not react with sodium hydroxide. Now, we are going to be moving on to the observations. You can see if you introduce wet litmus, wet blue color litmus into phenol. Now, students, over here you would observe that the phenol is colored in a slight hue of or slight pink or red color. The reason for this is normally phenols should be colorless or clear solutions without a particular color if it is obtained in pure form. However, if certain amount of impurities are present in the phenol that you obtain, it is going to be slightly pink red in color. That is why we use this color, because in your school laboratories, most of the time the phenol that you may come across might have this pink hue to it. So therefore, we indicated it with this particular pink color. However, a phenol would appear colorless if you can obtain the phenol in pure form. Now, let's move on to the test. If you take wet blue litmus paper and if you dip it in a small amount of phenol, you will observe that the blue litmus paper turns red. Now, students, keep in mind this red color is not going to be a strong red color compared to when blue litmus paper is reacted with a strong acid. However, you can see a noticeable change in the blue color of the litmus paper. It will change to a red color. Apart from that, students, you will see when it comes to adding alcohol, or when you are adding a blue litmus paper to alcohol, the color of the litmus paper will not change. Alcohols are extremely low in its acidity, so therefore it is not going to be sufficient enough to change the color of the blue litmus paper. Blue litmus paper will remain blue. It will not change its color to a red color. However, phenols will change the blue litmus paper's color to a red color. You can see the color of the blue litmus paper is starting to change. From blue, it has turned to a red color. Now, we move on to the summary of the test that we spoke of here. Or we can actually discuss what we spoke of here. We can see we used Benzene disonium chloride, which we have the structure of here. When we reacted benzene disonium chloride with phenol in alkaline medium, employing 0 to 5 degrees Celsius temperatures, we saw the formation of a orange color azo dye. So that was a test that we can do to identify phenol from alcohols. Why? Because alcohols will not show any observation. It will not react with benzene disonium chloride to give us a orange color azo dye. So therefore, we can actually use this test to identify phenols from alcohols. Then we have bromine water test. So if bromine water is added to phenol, they will react at room temperature, and immediately the bromine water, the color of bromine water, which is the brown color of bromine water, will be decolorized, and it will also proceed to form a white color precipitate. So bromine water will be decolorized, or the brown color of the bromine water will be decolorized, and very important, a white precipitate will be formed. Does alcohols show, or do alcohols show this reaction? No. Alcohols do not show the same observations, so we can use this test also to separately identify the two. Finally, if we add neutral FeCl3 to phenol, we saw the formation of a purple or violet color solution. However, we do not see such reactions with alcohols. After forming this violet color solution, if you add a little bit of HCl into that solution, we can see the violet color will be decolorized. We can see that the violet color will be decolorized. So this test can also be used to identify phenols from alcohols. Now students, we will be moving on to the experiment that we are going to conduct in the lab. So when it comes to experiment number 26, we will be requiring these chemicals and equipment. We have to have litmus paper, a water bath, a Bunsen burner. As for our equipments, when it comes to chemicals, we'll be using phenols. We will be using phenol, sodium hydroxide, dilute hydrochloric acid, sodium carbonate, liquid bromine, dilute ammonia solution, dilute ferric chloride solution, and alkaline potassium permanganate and sodium carbonate. Now again, we can see the same precautionary statement is given. Concentrated solutions of phenol are quite toxic and can cause severe skin burns. Very important to remember. So we are bringing it up again. Concentrated solutions of phenol are toxic, as well as it can cause severe skin burns. You should be very careful when it comes to handling this substance. If this substance comes into contact with your skin, it will cause skin burn. So therefore, you have to be very careful when handling this substance. Now, the very first test is taking a little bit of phenol separately into a test tube and add 1 cubic centimeter of water and shake. Test the solution with red and blue litmus paper. Now students, you know phenol when react with water will form phenoxide ion along with H3O plus. And the equilibrium position of this particular equilibrium lies more towards the right hand side. That means it produces more H pluses. So when you are trying to test a solution that is acidic with blue litmus paper, what will take place? You will see the blue litmus paper should turn into a red litmus paper. You can see as you introduce our blue litmus paper into the petri dish, it actually changes its color to a red color. So if you test the same phenol sample that we have in the petri dish with red litmus paper, will it change its color to a blue color? No. Phenol is acidic. Red litmus paper is used to test for a base. So red litmus paper will not change its color. Red litmus, red litmus paper will not show a color change. So this indicates that phenols are acidic. Then let's say take a little phenol separately into a test tube and add 1 cubic centimeter of water, and to that we are going to be adding bromine. After adding a little bit of water to phenol, we are going to be adding bromine to it. So now bromine, like we mentioned earlier, is going to be brown in color. Bromine is brown in color, or bromine water, and when you react it with phenol, it forms 2,4,6 tribromophenol. You can see at the second carbon, fourth carbon, and the sixth carbon, you can see there are 3 bromine groups connected to phenol. So we say 2,4,6 tribromophenol. 2,4,6 tribromophenol. This is going to be produced as a white color precipitate. As it doesn't dissolve well in water, it will precipitate out as a white color precipitate. Since bromine was used up to produce this compound, we will be observing the decolorization of the brown color of bromine. Bromine's brown color will be decolorized. So, two observations: brown color decolorization and formation of a white precipitate. This indicates the presence of phenol. Now, we are going to understand why this reaction is happening the way that we mentioned earlier. Reactivity of the benzene ring in phenols. The benzene ring in phenol is electron rich compared to benzene. The benzene ring in phenol is electron rich compared to benzene. Why is it electron rich compared to benzene? Because an OH group is attached directly to the benzene ring. Due to the delocalization of the lone pair of electrons on the oxygen atom over the benzene ring in phenol. Now we saw when we were drawing the resonance structures of phenol that oxygen that is directly connected to the benzene ring has lone pairs on it. And this lone pair of electrons, actually one lone pair of electrons in oxygen, can get delocalized into the delocalized electron cloud of benzene. Or since we mentioned the delocalized word twice, just to save you the confusion, we can say the lone pair of electrons on oxygen can get incorporated into the benzene's delocalized electron cloud. So then what happens to the stability of benzene? Actually, it goes up. And at the same time, the electron density of benzene also goes up. So this encourages electrophilic groups to attack benzene more. Why? Because now electron cloud of benzene is electron rich, or delocalized electron cloud of benzene is electron rich, or electron density is higher there. So electrophilic groups will be able to easily react with such benzene groups. So that is why we see when it comes to phenols, phenols easily react with bromine. But do benzene react easily with bromine? At room temperature, if you add bromine to benzene, does it form 2,4,6 tribromobenzene? No, because this will not happen, as benzene's electron cloud or benzene's delocalized electron cloud is not that high in its electron density compared to phenol's delocalized electron cloud. So they say, therefore, the benzene ring in phenol is more reactive towards electrophilic reagents than benzene itself. The OH group of phenol directs the electrophilic substitution to ortho and para positions with respect to phenolic OH group. So students, we saw when we spoke about phenol's resonance structures, one of the things that we saw was when the lone pair of electrons that we see in oxygen got donated here, these three positions, which we refer to as ortho and para positions, got the electron density around those locations increased quite a bit, to the point we actually wrote a negative charge on each of these positions that I have highlighted. If this carbon is number 1, 2, 3, 4, 5, and 6. In 2, 4, 6 carbons, the electron densities we observed were going up when the lone pair of electron in oxygen or on oxygen got donated to the benzene's delocalized electron cloud. We saw the electron densities in these three positions got increased. This is the reason why when it comes to nucleophilic, or when it comes to electrophilic, not nucleophilic, when it comes to electrophilic substitution reactions, we see electrophilic substitution or electrophilic groups attached mainly to ortho and para positions. We say that the phenolic group is actually a group that directs electrophilic groups to ortho and para locations of the phenol. When electrophilic substitution reactions of phenol are compared with the corresponding reactions of benzene along with relevant conditions, it is clear that benzene ring of phenol is more reactive. Benzene ring of phenol is more reactive towards electrophiles. Benzene ring of phenol is more reactive towards electrophiles. Again, this is because the delocalized electron cloud of benzene will receive a lone pair of electrons from the oxygen that is connected to the benzene ring. Therefore, electron density in that benzene ring will increase, which will activate the benzene ring further. This is why electrophiles are going to be attracted more towards phenol than towards benzene. Now, we are going to compare the reactions that we see in benzene versus phenol. Phenols react readily with bromine to form 2,4,6-tribromophenol, which is a white color precipitate, while benzene does not react with bromine. And we know at room temperature, if you react benzene with bromine, you will immediately form a white color precipitate. But what about benzene? Now, phenol and bromine will react immediately to form a white color precipitate. What about benzene and bromine? Does benzene and bromine react to form a white color precipitate? No. Benzene and bromine will not react to form a white color precipitate. This is because the reactivity of benzene is less than the reactivity of phenol. When this reaction is carried out with bromine water, 2,4,6-tribromophenol is observed as a white color precipitate, and this is only going to be observed in the first reaction. In the second reaction, we will not see this taking place, which tells us benzenes are less reactive when it comes to electrophilic substitution reactions, but phenols are more reactive when electrophilic substitution reactions are concerned. What about nitration? Another piece of evidence we can use to say why we think phenol is more reactive compared to benzene is that when it comes to nitration reaction, we observe these following observations. Let's dive into it. Nitration occurs even with dilute nitric acid at 20 degrees Celsius. So this is very important. Dilute nitric and 20 degrees Celsius. While benzene requires concentrated nitric acid along with a concentrated sulfuric acid and high temperatures. So see the differences. Nitration of phenol is done fairly easily. Actually, it produces two products, ortho substituted phenol and para substituted phenol. Now, if you observe here, when phenols are reacted with dilute nitric acid and when you conduct this experiment at 20 degrees Celsius even, you will see these two products forming. And if you observe closely, you can see the electrophilic substitution has taken place mainly in these two positions, the ortho and para positions. So, regardless of the positions, our main observation should lie here. You can see the temperature and the concentration of the reagent that we have used. We have employed low temperatures. Normally, when a reaction can take place at low temperatures, it indicates that the reaction is taking place with considerable ease. You can see over here we have employed higher temperatures. That means we need to increase or we need to provide energy for this reaction to take place. It is not happening with that much of ease. When it comes to the concentration of the reagents that we have used, we can see this first reaction with phenol can take place even with dilute nitric acid. And we don't need any other reagent over here. But you can see when it comes to benzene nitration reaction, we will be using concentrated nitric acid along with concentrated sulfuric acid, which indicates that when it comes to turning benzene into nitrobenzene, that this reaction is not going to happen that easily compared to the nitration of phenol. So this is evidence again that phenols are more reactive, especially when it comes to the electrophilic substitution reactions that are normally seen in benzene or any compound that is an aromatic compound. They normally take place through electrophilic substitution reactions, and these reactions can easily happen when it comes to phenol, but when it comes to benzene, you can see it is not going to happen that easily compared to how easily it happens with phenols. Now, it should be noted that Fiedel-Crafts alkylation reactions cannot be carried out with phenols because of the complex formation between Fiedel-Crafts catalyst and phenols. Now, since we are studying electrophilic substitution reactions here, when it comes to benzene and phenols, one thing that you should note is that you can't use Fiedel-Crafts alkylation reaction to compare how easily they react with benzene and phenols. Because with benzene, definitely, Fiedel-Crafts alkylation reactions can be done. However, you can't do the same with phenols. As mentioned here, there's a complex formation between phenol and Fiedel-Crafts catalyst. So therefore, Fiedel-Crafts alkylation reactions cannot be done when it comes to phenols. So you can't use that particular reaction to compare whether phenols are more reactive compared to benzenes. Students, now we are at the third point. Now the first point was where we tried to find out the acidity of phenol with the use of litmus paper. Then we reacted phenol with benzene. Right now we are trying to react phenol with sodium carbonate. Now students, we should remember when it comes to testing the acidity of a substance. Like I mentioned earlier, we normally talk about alcohol's acidity, phenol's acidity, and carboxylic acid's acidity. alcohols are only acidic enough to react with metallic sodium. When it comes to phenols, phenols can't react with sodium carbonate. Carboxylic acids, however, can react with all three of these: sodium, sodium hydroxide, and sodium carbonate. All of these three substances will show reactions with carboxylic acids. But when it comes to phenols, we will only see reactions with sodium and sodium hydroxide. Phenols will not give you a reaction with sodium carbonate. So that is what we are going to observe here as well. When phenols are reacting with sodium carbonate, since phenols are not acidic enough to react with sodium carbonate, you will not see a reaction between sodium carbonate and phenol. Now, how do we know that a reaction is not happening? We normally observe when an acid reacts with sodium carbonate, we will see the formation of bubbles, gas bubbles, effervescence. So you will not necessarily see the formation of gas bubbles here due to H plus or due to phenols not reacting with sodium carbonate. If phenol or if an acid is added, if we add a strong acid like HCl, or if we add a carboxylic acid like acetic acid, you will see sodium carbonate will react with the acid to produce carbonic acid. So carbonic acid is not a stable acid. It will dissociate into H2O and carbon dioxide. And carbon dioxide is produced as a gas, so therefore you will be seeing formation of gas bubbles in the medium as an observation. Since we don't have that observation here, this indicates that phenol did not react with sodium carbonate. Now, another observation that you would note is that phenol is an organic substance. It will not dissolve well in aqueous solutions. Although OH is polar, this large benzene group that we have here, the benzene group in phenol will not allow the phenol to dissolve in water. So therefore, when you are trying to dissolve phenol and water, one of the observations that you will be making is that phenol is not soluble in water. And if you are trying to react phenol with aqueous sodium carbonate solution, you will not see a single layer being formed. You will see a layer separation. You will observe a layer separation. So this layer separation indicates there is no reaction between the two as well. Because if this reaction took place, since phenol is converted into phenoxide anion, which is soluble in water, these two layers should mix together to form a single layer. So having two layers separated like this, even in the presence of aqueous sodium carbonate, indicates that sodium carbonate did not react with phenol. There is no reaction between phenols and sodium carbonate. This indicates that phenols are less acidic compared to carbonic acid. So this statement is a very important statement. It says phenols are less acidic compared to carbonic acid. Now, to observe why this statement is important, we will have to write down an equation that we expect to see when phenols react with the carbonate ion that we have in the medium. So first of all, if you take a strong acid like HCl, when it reacts with carbonate, you will see the formation of H2O and carbon dioxide, along with, in this case, Cl minus will also be seen. Now students, this H2O and carbon dioxide was formed due to the carbonic acid breaking down into forming water and carbon dioxide. The reason for that is carbonic acid is unstable. Carbonic acid is unstable. So therefore, in the presence of HCl, or if you balance this off properly, this 2HCl is raided and you'll be forming 2Cl minus. However, the main point here is when H plus from HCl comes into contact with the carbonate ion, it will turn carbonate into carbonic acid, which is unstable, and therefore it will form water and carbon dioxide. So this anion that is formed from the carbonic acid actually displaces as the acid in the presence of a stronger acid like HCl. So to displace the carbonic acid from the carbonate anion, a strong acid has to be in the medium. So you can think of it like this is a weak acid's anion, right? What you have here is what I'm highlighting here in red is the weak acid's anion. And when a strong acid like HCl is in the medium, the weak acid's anion gets displaced as the acid. But unfortunately, since the acid is unstable, you can see the formation of water and carbon dioxide instead. So to displace carbonic acid, whatever the acid that is in the medium reacting with the carbonate should be stronger than the carbonic acid. Otherwise, the carbonate will not get displaced as carbonic acid. So when you see the reaction between phenol and carbonate ions do not take place as we expect, or when phenols are not reacting with carbonate, we identify the fact that phenols are less acidic compared to the carbonic acid. Because if phenols were stronger than carbonic acid when it comes to its acidity, or if phenol had a higher acidity than carbonic acid, in the presence of this weak acid's anion, phenol will dissociate and allow the weak acid's anion to get displaced as the acid. However, since that is not happening, we can conclude that phenol is a weaker acid than the carbonic acid we have here. So students, that is the explanation to this particular statement. Phenols are less acidic compared to carbonic acid. The reason being, phenols are not capable of displacing this carbonate as carbonic acid because phenols are weaker than carbonic acid. Now, let's move on to the next slide. In the next slide, we also mentioned the same thing. You can see here. Sodium carbonate solutions do not react with phenols. Therefore, a layer separation can be observed. Similarly, sodium bicarbonate will also not react with phenols. So if you add sodium bicarbonate and phenols together, we do not see observation or we do not see the formation of gas bubbles. This indicates that bicarbonate ions also do not react with phenols. Just like in the previous scenario, you will see a layer separation and you will see that the two layers don't get mixed or they will not form just a single layer. Instead, they form two layers. So this observation confirms the fact that bicarbonates do not react with phenols and carbonates do not react with phenols. The main reason behind both of these situations is the fact that phenols are less acidic than carbonic acid. And one of the reasons why we always draw phenol at the bottom of the test tube is because phenol has a higher density than water, right? So when you are mixing two substances together or two liquids together, one of the questions that we get asked the most is the organic layer always going to be on the top. A lot of the students associate organic solvents or organic layers to be somewhat like oil. When you mix oil and water, oil layers mostly are on the top layer. So majority of the time some students inquire whether the organic layer or is always supposed to be on top. No, it all depends on the density of the liquid. The denser liquid will always sink to the bottom, and the less dense liquid will be on the top. So in this case, we can see water's density is 1 grams per centimeters cube, and when it comes to phenol, it's 1.07 grams per centimeters cube. So because of that, phenol will sink to the bottom. Now, we are going to be taking a look at the fourth step. Take a little phenol separately into test tubes and add 1 cubic centimeter of water, and then add a small volume of sodium hydroxide solution. So we are going to add sodium hydroxide to this. So when you add sodium hydroxide, students, this is going to react with phenol. Why does sodium hydroxide react with phenol? Phenol, although is not extremely acidic, it is still acidic. Therefore, and we observed earlier also, when it comes to alcohols, they only react with metallic sodium, and we discussed that phenols do react with metallic sodium, and then it reacts with sodium hydroxide as well. Only thing that it does not react with is sodium carbonate. So when it comes to phenols, it will react with sodium hydroxide and will produce sodium phenoxide. So sodium phenoxide salt is water soluble. Now, how do we know that it is water soluble, students? When you add a little bit of water to phenol, you can see as you add water to phenol, we'll select this in a different color. We'll indicate that in a different color. We'll take purple. You can see when it comes to phenol being added with water, the phenol water mixture will be present with 2 layers. The water layer again will be observed on the top, and the phenol layer will be at the bottom of the test tube. So this is because water and phenol do not react with one another that much, and they do not dissolve in one another well. Phenol is immiscible in water. Therefore, we will see a layer separation. However, when you add sodium hydroxide, what takes place is that phenol will react with sodium hydroxide, releasing the hydrogen on its OH group. Releasing this hydrogen on its OH group, phenol will react with sodium hydroxide. This will produce sodium phenoxide ion. You can see there's a negative charge on oxygen and sodium has its positive charge. So this is referred to as sodium phenoxide ion, and that will dissolve in water. That's a aqueous solution that you are going to be forming. So the layer separation will disappear once you add sodium hydroxide and dissolve the phenol. Now, with this observation in mind, let's move on to the next slide. We can see the reaction that takes place here very clearly. Phenol, sodium hydroxide, produces sodium phenoxide. This is the name of the compound, sodium phenoxide. Along with it, since there's a neutralization reaction is taking place, we will form small amount of water as well. Hydrogen from OH group that we have on phenol and the hydroxide ion from sodium hydroxide will come together to form water. In this reaction, the OH bond dissociates to form an alkaline salt solution, which is sodium phenoxide. Now they say very clearly this is an alkaline salt. Now why is it referred to as an alkaline salt? This is a reaction between a strong base and a weak acid. Phenol is a weak acid. However, Sodium hydroxide is a strong base. So when a weak acid and a strong base produces a salt, the salt that is produced is going to have the characteristic features of the stronger species that reacted to form it. So out of the two reactants, which one had the stronger properties? The base did. So therefore, the salt that is formed here is going to be basic or alkaline. So therefore, when a strong acid and a weak base reacts, the product that you form is going to be basic, or product is going to be an alkaline salt. When it comes to a strong acid reacting with a weak base, the salt that is produced is going to be an acidic salt. So that is something that you should keep in mind. And we have a summary slide here. So if you take a look at this slide, we can take a look at the summary of what we did. We have phenol. Phenol reacting with water. We will observe that it is immiscible in water and there will be layer separation. Phenol and water do not react with one another or do not get mixed with one another. Phenol and water does show an equilibrium where phenoxide ion and H3O plus is formed. However, phenol and water does not get mixed that well. So they are immiscible, will form two separate layers. When it comes to phenol reacting with sodium hydroxide, you'll be forming sodium phenoxide. This is an alkaline salt, and you will not observe a layer separation because the resultant phenoxide ion is going to be a water soluble ion. So the resultant sodium phenoxide is going to be water soluble. Therefore, you will not see two layers being formed. Instead, the two layers will turn into one when sodium hydroxide is added to the mixture. What about sodium bicarbonate solution? Again, sodium bicarbonate is introduced as an aqueous solution. However, phenol does not show any reaction between sodium bicarbonate or sodium carbonate. And in both of these instances, you can see the result is the same. You will observe that these two solutions, since they are in aqueous medium, phenol is immiscible in these aqueous solutions and therefore there will be layer separation. So these are the observations that we made while conducting this experiment. Now let's move on to our next slide. Now we are at the fifth point, preparation of neutral FeCl3. Now students, we are going to be looking at the reaction between neutral FeCl3 and phenol. Now in the theory part we discussed when neutral FeCl3 and phenol are reacted with one another, it produces a violet solution. So in order for us to get to this observation, it is important that we produce a neutral FeCl3 solution. And first of all, we will read this paragraph that we have here. To a solution of dilute FeCl3 solution, add dilute ammonia until a faint permanent precipitation of ferric hydroxide is formed. Now we have our ferric chloride. We dissolve it in water. We have the ferric chloride solution now. And to this ferric chloride solution, we are going to add a little bit of dilute ammonia until we observe ferric hydroxide, which is a red-brown precipitate, being formed. Afterwards, students, we are going to filter this solution to remove the brown ferric hydroxide precipitate, and the filtrate that we obtain after filtering off the ferric hydroxide precipitate is going to be our neutral ferric chloride solution. And the neutral ferric chloride solution is going to be yellowish brown or brownish yellow in color. So the neutral FeCl3 solution is going to be brownish yellow in color. So they have given the equation here. FeCl3 aqueous, when reacting with sodium hydroxide, will produce FeOH3, which is ferric hydroxide, which is a red-brown color precipitate. Now, students, you must be wondering, what do you exactly mean when you say a neutral FeCl3 is formed? Isn't ferric chloride already neutral? The answer to that question would be no. Ferric chloride solutions are actually having an acidic pH to it. Due to the small size and the large charge of the Fe3 plus ion, students, Fe3 plus ions, when they are in water, they form the compound that we see here, which is going to be, give me a second, in water, our Fe3 plus ions have this complex ion formed, FeH2O 6 3 plus. However, students, this particular complex is not going to be present in the medium for long, because Fe has a very small ionic radius, or Fe3 plus has a very small ionic radius, and the charge density on this particular ion is quite high, that it pulls the water molecules towards it strongly enough until a deprotonation reaction happens. Now, students, although we write the Fe3 plus ions in aqueous medium has this complex actually changes the complex that I'm about to write due to deprotonation of a water molecule that we have over here. So out of the 6 water ligands that we observe here, one can undergo a deprotonation to produce this complex, H2O5 and OH. Now, this mainly happens due to the higher charge density on Fe3 plus. As you know, Fe3 plus has a smaller ionic radii as well as a high charge. So therefore, it contains a high charge density, which pulls the water ligands closer to itself. And when this is taking place, a water ligand can actually undergo a deprotonation reaction. However, it doesn't stop here. It can again, if you take this compound or this complex that we have mentioned just now, H2O5 with one OH ligand, can actually turn into another complex. A second water molecule can also undergo deprotonation, producing the complex that I'm writing right now. So these two complexes that we see over here are yellow-brown in color. That is why when it comes to Fe3 plus aqueous ion solution, we observe the yellow-brown color as well. But as these reactions are taking place, one of the things that you observe is that when the deprotonation reaction takes place, an H plus is removed. And when a second water molecule also undergoes deprotonation, another H plus is going to be removed. So what this means is the solution is going to be acidic, as Fe3 plus ions deprotonate water molecules. H plus ions are going to be introduced into the medium, making the solution more and more acidic. Because of that, a solution of Fe3 plus aqueous ions are going to be acidic. When you dissolve ferric chloride in water, you are going to obtain a solution that has a lower pH than pH 7. So we need to make this solution neutral. How do we make it neutral? By adding ammonium hydroxide. Why do we add ammonium hydroxide? Because it's a weak base. So since it's a weak base, it is not going to drastically react with the Fe ions that we have in the medium and form ferric hydroxide. It's going to reduce only a controlled amount of OH minus ions. So when initially OH minus ions come into the medium, these OH minus ions that enter the medium will initially react with the additional H plus ions or H plus ions in the medium and will get neutralized as water. Then, after H plus ions are removed from the medium, the next incoming OH minus ions will react with Fe 3 plus ions in the medium. And we are only adding OH minus ions very carefully. We only add OH minus ions very carefully until we observe a small amount of FeOH3 or ferric hydroxide is formed. We don't want to precipitate out all of the Fe3 plus ions. So we will only add ammonium hydroxide until we see the formation of a very small amount of ferric hydroxide. We don't want to precipitate out all of the Fe3 plus ions in the medium. So the reason why we're adding ammonium hydroxide very carefully is to make sure first all of the H plus ions in the medium get reacted and turned into water. So now after all of the H plus ions are gone, solution is now neutral. And how do we identify that the solution is neutral? Because when there is no more H plus ions to react with OH minus ions in the medium, OH minus ions will start to react with Fe3 plus, and we will see the formation of a red-brown precipitate, which is ferric hydroxide. So at that point we know all of the H plus ions in the medium are now gone, which will indicate that the solution is neutral. Afterwards, we can actually proceed to carrying out the reaction between neutral FeCl3 and phenol. You can see afterwards you can take few drops of neutral FeCl3 solution and observe the color change. So you have to add a few drops of FeCl3 to phenol and observe a color change. First thing that you're going to observe is you will form a violet color solution. As I mentioned in the initial lesson, when you are reacting phenol with neutral FeCl3, due to the presence of phenoxide ion in the medium along with FeCl3 or Fe3 plus ions, Fe3 plus ions and phenoxide ions together form a complex which happens to be violet in color. So you form a violet color complex in the presence of Fe3 plus ions and phenoxide ion. Now you know if the solution was acidic, in an acidic environment, formation of phenoxide ion, even in lower concentrations, will be difficult. So the observation of this particular color will not take place. So that is why we need a neutral FeCl3 solution. If we took the FeCl3 that is not neutral, it will be having enough and more H plus ions in the medium. We should make it difficult for phenol to dissociate into H plus and phenoxide ion. And to give this violet color, phenoxide ion should be present in the medium. So in the presence of phenoxide ion and Fe3 plus ions, we will see the violet color. And afterwards, students, when this solution is treated with HCl, they say to this solution add a few drops of HCl and observe the color change. So as you add a few drops of HCl to this medium, as I mentioned earlier, H plus ion concentration will go up. as H plus ion concentration goes up, phenoxide ion will turn back into phenol. Now, this will decrease the phenoxide ion concentration in the medium to the point where you will not form a complex between Fe3 plus ions and phenoxide ions, because the phenoxide ions in the medium will actually completely turn into phenol. So when there is no phenoxide ions in the medium, you will not observe this violet color complex. So it will be decolorized. The violet color in this particular solution will be decolorized as you convert the phenoxide ions in the medium to phenol through the addition of HCl. Apart from what we just learned, another thing that you should keep in mind, or which is going to be important, is that if you take salicylic acid, now salicylic acid is when a COOH group is attached to an ortho position of a phenol. So when a salicylic acid is reacted with neutral FeCl3, you are going to observe the violet color formation. So when a salicylic acid is reacted with neutral ferric chloride solution, a violet color will be observed. And just like in the previous observation, when HCl is added, violet color will get decolorized. When HCl is added, the violet color will get decolorized just like in the previous instance. So not only phenols, other compounds like salicylic acid also give us the same observation, which is formation of a complex which happens to be violet in color. And then when you add a little bit of HCl, you can see the violet color will get decolorized. When neutral FeCl3 is treated with benzoic acid, now we don't have a phenol group in benzoic acid, if you can observe here. When it comes to benzoic acid, we don't have a phenol group. However, even with benzoic acid, when you react neutral FeCl3, what is going to happen is, in aqueous medium, benzoic acid will be producing benzoate anion, and FeCl3 will be introducing Fe3 plus cation. So in the presence of this Fe3 plus cation and benzoate anion, a violet color complex can be formed. So just like in previous instances, when neutral FeCl3 is reacted with benzoic acid, you will observe the formation of a violet color solution. However, the second observation is going to be different. However, unlike phenols or salicylic acid, when the resultant solution is reacted with HCl, benzoic acid will be formed again, forming a white color precipitate. So students, like I mentioned earlier, when you are reacting HCl, you will not see the same observations you observed before when it comes to phenols and salicylic acid. When it comes to benzoic acid, after you add HCl to this violet color solution, what you are going to observe is the decolorization of the violet color along with a white color precipitate being formed. Now, why do we observe the formation of a white color precipitate? As you know, benzoic acid is not soluble in water. So as you add an acid into the medium, you know the benzoate anion will react with the H plus in the medium to form benzoic acid. And the formed benzoic acid is water insoluble, creating a white color precipitate. So this is the observation when you react benzoic acid with neutral FeCl3 and then add HCl to it. But when it comes to phenol when reacted with neutral FeCl3, we saw the formation of a violet color, and then when we add HCl to it, the violet color got decolorized. There was no white color precipitate formed. When it comes to this instance, you will see the formation of a white color precipitate. Now, let's take a look at the summary when it comes to how neutral FeCl3 can be used to identify phenols. Now, when it comes to FeCl3 reacting with phenol, a purple color solution is formed. When added with HCl to that resultant solution, purple color will decolorize. When it comes to salicylic acid, we can see the same observations. Purple color, and afterwards the purple color gets decolorized. Finally, when it comes to carboxylic acid, we can see in the presence of carboxylic acid and neutral FeCl3, a purple color is formed. However, when dilute HCl is added, an additional observation is made apart from the decolorization of the purple color or violet color. You can see a white color precipitate is also going to be formed. So this violet color decolorizes and a white color precipitate will also be formed. Now students, when it comes to the reaction between phenol and FeCl3, it's a very important reaction. I want you to remember these observations. Neutral FeCl3 is going to be yellowish brown in color, and when you add FeCl3 to phenol, you are going to have a violet color solution which is going to get decolorized upon the addition of HCl. These are the tests that you can use to identify the presence of phenol. As a summary, let's go through the tests that we conducted today to identify the presence of phenol. You can take phenol and add a little bit of water to it. You saw a layer separation. Phenol is immiscible in water. You can see the layer separation when you add phenol and water together. Then, if you add sodium hydroxide to this mixture, you can see the two layers will start to mix. This is due to formation of the phenoxide anion in the presence of sodium hydroxide, which is going to produce sodium phenoxide, which is soluble in water. Afterwards, if you take another phenol sample and react with bromine water, which is brown in color, you can see the color of bromine water will decolorize in the presence of phenol, which indicates that phenol reacts with bromine water. Actually, what is produced is going to be 2,4,6 tribromophenol, which happens to be a white color precipitate. So apart from the decolorization of bromine, you will see the formation of a white color precipitate. Then we moved on to adding sodium carbonate and sodium bicarbonate to phenol. If you add a sodium carbonate solution to phenol, you can see there is going to be layer separation. Phenol and sodium carbonate do not react with one another. It is confirmation that it does not react with one another. We can get a confirmation through not observing the formation of bubbles. There is no bubble formation indicating phenol did not react with sodium carbonate. The same observation can be made when it comes to sodium bicarbonate as well. And afterwards, finally, when you react phenol with neutral FeCl3, you see the formation of a violet color solution. If you take a portion of that violet color solution and react it with HCl, you can see this violet color gets decolorized. So these are the observations that we made with phenol. So students, now we have gone through the theory parts related to this particular practical. It's time that we moved on into the lab to conduct these experiments. Let's see you at the lab. GCE Advanced Level Chemistry Practical Series, experiment number 26. Examination of properties of phenol. In this practical, we are going to observe the acidic nature of phenols and what chemical reactions that revolve around phenols. Keep in mind, when handling phenol, you have to be very careful. It is toxic, and when you are handling phenols, always wear gloves and make sure that it does not come into contact with your skin. Now, let's move on to our reagents. For this practical, we will be using these chemical reagents and these equipment. We have here phenol, we have bromine water, we have sodium carbonate, sodium hydroxide, ferric chloride, and dilute ammonia. Apart from those chemical reagents, we will be using droppers, test tubes, two beakers, and we have our red litmus, our blue litmus, and pH paper. We will be using a filter paper, a funnel, and a retort stand. Now, let's move on to our first part of this experiment. Let's start with the first part of our practical. We are going to observe the solubility of phenol in water, and then we will be testing the pH value of a phenol solution. We will be taking a test tube, and let's take a small amount of phenol into our test tube. This is enough. Now, you will observe the color of the phenol that we have in this test tube is between a pink and a red color. This color is there because the phenol that we have in this test tube is not 100% pure. A 100% pure sample of phenol will appear to be colorless, but if there are any impurities present, the color you will be observing is this, a pink-red color. Now, let's add a small amount of water to this and see whether this phenol sample dissolves in water. We will be using a wash bottle for that, and we will be adding a small amount of water very carefully. At first glance, you would see a layer separation. You can see the phenol layer at the bottom and the water layer at the top. The phenol layer will sink to the bottom as phenol has a higher density than water. So therefore, you will observe the phenol layer at the bottom and the water layer at the top. However, phenol is known to be moderately soluble in water. 8.3 grams of phenol can dissolve in 100 milliliters of water. So this is a moderately soluble organic substance, which means some amount of this phenol will dissolve if I shake this test tube. As you can see, upon shaking the test tube, most of the phenol did dissolve in water. However, there is still a small portion of phenol that is not dissolved in water. So this indicates that phenol is moderately soluble in water, and it dissolves in water to form a phenol solution. Now, this is due to the presence of OH group connected to the benzene group. This allows phenol to be moderately soluble in water. Now, let's check the pH of this mixture. In this part of the experiment, we are going to see the acidity or the basicity of our phenol solution. In order to do that, we will be using a red litmus paper and a blue litmus paper. Later on, we will be using a pH paper to determine the pH value of this phenol solution. Red litmus paper will turn blue in the presence of a base. Blue litmus paper will turn red in the presence of an acid. And we have here a control. So this blue litmus paper is there to give you an idea what the color change would be when it is added with water. Keep in mind, water is neutral, so therefore the pH paper should not change its color, but it will give you an idea when water is added, when the pH paper get wet, what the color you observe will be. So without further ado, let's add a small amount of the phenol solution into our red litmus paper and to our blue litmus paper. And then let's add a little bit of water into our control. As you can see, the color of the red litmus paper did not change. It remained red. However, the color of the blue litmus paper changed slightly to a red color. So to see this color change very clearly, we can compare the blue litmus paper that was made wet with distilled water. You can see normally when the blue litmus paper is made wet, it is going to be remaining blue, but you can see the blue litmus paper added with the phenol solution has turned red. So very clearly we can see now the color change that has taken place in our blue litmus paper, because we can compare it against the control where we added a little bit of water to a piece of blue litmus paper. Now you would not see a very dark red color in the blue litmus paper, as phenol is not a strong acid. It is not going to be indicating strong acidic properties. So that is why the color change you see in the blue litmus paper is not very prominent. Now let's move on to our pH paper. We have our pH paper book here, and we'll take a pH paper out of that book, and let's add a small amount of phenol solution into our pH paper. As you can see, when you added small amount of phenol solution into our pH paper, the color that the pH paper turns to is somewhere between yellow and red. It is an orange color between yellow that you observe here and red here, which means the pH of this solution, phenol solution, is somewhere between pH 3 and pH 5. This is not red and this is not yellow. It is between red and yellow, which means the pH of the phenol solution we have is between pH 3 and pH 5. Now let's move on to the summary. We observed that phenol was moderately soluble in water. 8.3 grams of phenol can dissolve in 100 milliliters of water. And apart from that, we noticed the phenol solution that we made is slightly acidic. We observe this with the use of litmus paper. We saw the red litmus paper did not change into a blue color, indicating that this in fact is acidic, and the blue litmus paper turned into a red color, confirming that the phenol solution we have here is acidic. Then we moved on to adding the phenol solution onto a pH paper, and the pH paper turned to an orange color, a color between red and yellow. This indicated the pH of the phenol solution is somewhere between pH 3 and pH 5. Now, let's move on to the next part in this experiment. In this part of our experiment, we are going to see how bromine or bromine water reacts with phenol. Now, to test this, we will take a test tube and take a small amount of phenol into this test tube. We will use this test tube to add a small amount of phenol into our bromine water because I want to compare the colors of the two solutions you will have. Now, we have our bromine water solution. Now, if you take liquid bromine, it will appear brown or red-brown in color. Now, this is appearing a yellow color because we have bromine water here. If you take liquid bromine, the color of liquid bromine will be red-brown. What we have here is bromine water, and you can see a yellow color in this bromine water sample we have here. The color of this bromine water is due to the presence of Br2 in this sample. Now, let's add a small amount of phenol into our bromine water. Observe the color of phenol. Due to the impurities present in this phenol sample, we can see it is pink or pinkish red in color. Now, let's add this phenol into our bromine water. As you can see, upon addition of phenol into bromine, you can see the color of bromine water disappeared. At the same time, I hope you can see the formation of a white color precipitate or white color powdery substance inside this reaction mixture. What happens here is when phenol is added to bromine water, the bromine reacts with phenol to form tribromophenol, which is insoluble in water, which is a white color precipitate. So, the color of the bromine water disappeared and it formed a white color precipitate that is suspended in the aqueous medium here. Now, let's add a little bit more bromine water to see whether we can see a change in color or whether we can see a bit more precipitate forming here. As you can see, when I add more and more bromine, the precipitate that is formed increases. The precipitate that you see here is 2,4,6 tribromophenol. 2,4,6 tribromophenol. Now, for comparison, let's take a small amount of bromine water and compare the two colors. Bromine water was yellow in color, and now you can see after adding phenol to this bromine water, we saw the color of bromine water disappeared, as well as a white color precipitate started to form, which is 2,4,6 tribromophenol. We'll add this sample of bromine also into this mixture. You can see even addition of that portion of bromine water did not change the color of the mixture over here. It remained colorless, and at the bottom what you can see is the portion of phenol that is insoluble in water. And in this section of the test tube, you can see the bromine water that was present completely decolorized and formed a white color precipitate which is insoluble in water due to reaction with bromine and phenol. In that test, what took place was when bromine came into contact with phenol, as phenol is quite reactive, it reacted well with bromine and formed 2,4,6 tribromophenol, which is insoluble in water, and due to this reaction the color of bromine water got decolorized, and due to the product being insoluble in water, we saw the formation of a white color precipitate. You can see the precipitate sinking down to the bottom. In this part of our practical, we are going to see how phenol reacts with sodium carbonate. We need to observe if phenol is acidic enough to have a reaction with sodium carbonate. Now, we will be taking sodium carbonate solution for this. Let's take a test tube and add a small amount of sodium carbonate into our test tube. We have our sodium carbonate solution here. Let's take our phenol and add a small amount of phenol into this sodium carbonate. As you can see, upon addition of phenol into our sodium carbonate solution, they did not mix. There is clearly a separation, and if you mix it a little bit, you will see some amount of phenol will dissolve in the aqueous medium like we have observed before, but we do not see evolution of a gas. When sodium carbonate is reacted with an acid, we see the formation of carbon dioxide gas. Carbonate anion will react with the H pluses and will form carbon dioxide and water. In this reaction, we saw when you mixed phenol with sodium carbonate, and when we mixed it well, we did not see any gas evolving from this mixture, indicating that phenol did not react with the carbonate anion. So therefore, we do not see formation of carbon dioxide gas. We did not observe any bubble formation or effervescence in this mixture. And the color of the phenol still persists, indicating phenol did not become phenoxide ion, because when phenol releases the H plus ions attached to the OH group, it forms phenoxide ion. This will allow the phenol to dissolve in water. You can see the layer separation is still very clear, indicating it did not react with sodium carbonate. This tells us phenol is not acidic enough to show a reaction between sodium carbonate or sodium bicarbonate. Now, let's move on to our next test. In this part of our test, we are going to see the reaction between phenol and sodium hydroxide. First, let's take a small amount of phenol into our test tube. We have our phenol here. And to our phenol sample here, let's add a little bit of water. We will add a small amount of distilled water with the help of a wash bottle. You can see before mixing, you can see a little bit of layer separation here. We saw phenol is moderately soluble in water, but if I don't mix it, you will see the two layers separated like so. Now to this phenol solution, let's add a small amount of sodium hydroxide and see what the observations are. Note what happens when sodium hydroxide is added to this mixture. As you can see, when sodium hydroxide is added, and if you shake it, the phenol that did not really dissolve in water earlier starts to mix well with sodium hydroxide. But now, after sodium hydroxide is added, you can see it entirely dissolved in the presence of sodium hydroxide and formed a clear solution. When you added just water, we saw a layer separation, but when we added sodium hydroxide and mixed it, we saw the layer separation ceases to exist and the phenol dissolves well in sodium hydroxide. The reason for this is the reaction that takes place between phenol and sodium hydroxide. Phenol is slightly acidic, so in the presence of sodium hydroxide, phenol reacts with sodium hydroxide and forms sodium phenoxide. The OH minus ions from sodium hydroxide reacts with the H plus that is released from phenol, and phenol produces phenoxide ions, and together with the sodium plus ions in the medium, they will form sodium phenoxide. Therefore, the phenoxide ion is soluble in water. You can see there's no layer separation, as well as you can see a clear solution has been formed when we react sodium hydroxide with water. Now, let's do the same test, but before we add sodium hydroxide, let's add a small amount of phenol and add a small amount of water, and let's mix it really well. We can see some amount of phenol dissolves in water and creates this cloudy solution. And to this phenol solution, let's add sodium hydroxide. As you can see, when sodium hydroxide is added little by little, the cloudy nature of the phenol solution disappears and it forms a clear solution. Now, if you mix it really well, you can see the phenol completely dissolves in sodium hydroxide and forms a clear solution. This is again because of formation of phenoxide anion. Although phenol is moderately soluble in water, phenoxide anion is soluble in water. Therefore, you will see the formation of a clear solution that has a slight pink hue to it. However, we will see the formation of a clear solution when sodium hydroxide is reacted with phenol. Now, let's move on to the next part of our experiment. In this part of our practical, we are going to observe how ferric chloride reacts with phenol. This is an acidic salt. Therefore, we need to react the ferric chloride solution with dilute ammonia and produce a neutral ferric chloride solution. First, let's observe the pH of ferric chloride solution. We will take our ferric chloride solution and we will test it with the use of a pH paper. We will take our pH paper to this pH paper, we will add a drop of ferric chloride. Let's see what happens when a drop of ferric chloride is added to our pH paper. As you can see, the color of the pH paper turned a red color. Let's compare this color against the pH guide provided with a pH paper booklet. Now, let's observe what color we see here in this pH paper. It is certainly not pH 1. It does not align well with pH 2 as well. It is very close to pH 3, and if you compare it against pH 4, you will see not very close to pH 4. So, this must be having a pH of around pH 3. It does not perfectly align with the color. However, this color indicates it is very close to pH 3. That means the ferric chloride solution we have here has a pH of around pH 3. Now, let's move on to preparing a neutral ferric chloride solution. For that, we will be using a beaker. Let's use our ferric chloride solution. We'll transfer the ferric chloride solution into a beaker. As you can see, you can observe the color, the brown or orange brown color very clearly. Now, to this, we will be adding dilute ammonium hydroxide or dilute ammonia. We will add dilute ammonia drop by drop until we observe a brown color precipitate. When you add ammonium hydroxide, you can see before mixing it the formation of a brown color precipitate. But if you mix it, you might see it disappearing. We'll add a few more drops of ammonium hydroxide. If you observe a persistent brown color precipitate forming, that indicates the presence of ferric hydroxide. We still can't see a persistent precipitate here, meaning we should add more ammonium hydroxide. So what happens here is, since the medium is acidic, when you are adding ammonium hydroxide, the hydroxide ions reacts with the acid H plus ions, or hydroxide ions react with the H plus ions and remove the H plus ions from the aqueous medium. And thereby we make the ferric chloride solution neutral. But after all of the H plus ions are removed from the medium, the additional ammonium hydroxide that is added to the medium will give us a ferric hydroxide precipitate, a brown color ferric hydroxide precipitate. This indicates that we should stop adding ammonium hydroxide and start filtering the solution to obtain the neutral ferric chloride solution. We still cannot see a precipitate, so let's add a few more drops. Now you can see the formation of ferric hydroxide precipitate. Very fine precipitate is formed here. I'm not sure whether the camera can capture it. However, a fine ferric chloride precipitate is formed here. Before we move on to filtering the solution, we can double check if we have formed a neutral solution by using a pH paper. We have our pH paper here. Let's add a drop of neutral ferric chloride here to see if the solution has actually become neutral. As you can see, when we are adding dilute ammonia into this, the color of the solution starts to change, and you can see a brown color precipitate has started to form. You can see it coating the walls when I mix it, indicating that we have our brown color precipitate ferric hydroxide. So now let's filter the precipitate out from this suspension, and we'll obtain the supernatant of this suspension. The supernatant is going to be neutral ferric chloride solution. So in order to filter this precipitate out from this suspension, we will be using a filter paper such as this, and we will be using this setup. So we have our funnel set up here, connected to a retort stand holding up the funnel, which will be allowing the filtrate to be filtered out into a beaker. Now, when you are using a filter paper, you have to make sure that you use it the right way. We have to fold it
once in half like this. Then you can fold it again in half, and you will be folding it once more. You can fold it one more time. Now, after you have folded it like this, you will be unfolding it, and you will arrange it in a manner like this. You have to make sure that you keep folding it in the right manner, that you like you see over here, so that you can create an open structure that will allow the suspension to be filtered properly. So once you have done that, you can open it up like this. Now this will increase the surface area that is going to be used for the filtering process. So when you have a filter paper folded up like this will increase the surface area that is used for filtering of this suspension. So now I will place this filter paper on top of our funnel, and now after placing our filter paper on the funnel, we can wet the filter paper with a little bit of distilled water. This will fix the filter paper in place and will allow the filtering process to be a little bit more efficient. So after wetting our filter paper, we will start transferring our suspension onto our filter paper. We'll make sure the suspension is mixed really well, and then we will transfer it onto our filter paper. As you can see, when we transfer some of our suspension onto this filtering mechanism, you can see the solution is separated from the precipitate. On the filter paper, you will see ferric hydroxide precipitate remaining, and filter paper will filter out the ferric chloride neutral solution. So what you have here in the beaker is our ferric chloride neutral solution. Let's filter out the ferric chloride neutral solution completely, and I will show you the brown color precipitate that we have on our filter paper. That brown color precipitate that you will be seeing on the filter paper is ferric hydroxide. You can see the filter paper is now coated with a brown color precipitate. That is our ferric hydroxide, and in our beaker is a supernatant or the filtrate that is going to be our ferric chloride neutral solution. Now, we have allowed the filtration to happen for a while now, and you can see, if you take a look at the top view, we can see the brown color precipitate remaining on the filter paper. What you see here is ferric hydroxide precipitate, which is a brown color precipitate, and you can see at the bottom the filtrate is a yellow orange color. This is due to the presence of Fe3 plus ions. We have our neutral ferric chloride solution here. Neutral ferric chloride solution is present here. The precipitate is present in the filter paper. The ferric hydroxide precipitate is present on the filter paper, and the filtrate will contain our neutral ferric chloride solution. Now, let's add phenol to this ferric chloride solution and see what we would observe. We will take a test tube, and to this test tube I'll be taking a small amount of ferric chloride solution. This is our neutral ferric chloride solution. Now we have our neutral ferric chloride solution here. Now to this, let's add a small amount of phenol. Let's add a drop of phenol. As you can see, when we add a small amount of phenol, the color of this solution is starting to change. I have not yet shaken it, but you can see a violet color forming when we add phenol to our ferric chloride solution. Let's mix it to see the color very clearly. As you can see, a violet color solution was formed. Normally you saw phenol was not dissolving very well with water, but you can see here all of the phenol that we added dissolved really well and produced a violet color solution. Now, this violet color solution was formed due to phenol reacting with ferric chloride solution and forming phenoxide anions. The phenoxide anion and Fe3 plus ions form a complex that is purple in color, or that is violet in color. That is why you observe a violet color when you react neutral ferric chloride with phenol. So we can use this test to identify phenol. If you react neutral ferric chloride with phenol, you will see the formation of a complex between Fe3 plus ions and phenoxide anions, which is violet in color. This could be used as an identification test for phenol. And now we are going to add a small amount of hydrochloric acid to observe what happens when we acidify this medium. We will take our hydrochloric acid. We have here our hydrochloric acid. To this, to our purple color solution we have here, let's add a small amount of hydrochloric acid. Observe what happens when hydrochloric acid is added. What happens to the color? What is your observation? the color of the solution is starting to disappear. And we are noticing the color that we had earlier. Initially, when we were starting this experiment, we saw the ferric chloride neutral solution we took to our test tube had the same color, but when we reacted it with phenol, we saw the color turn to a purple or a violet color. But upon addition of HCl, this violet color disappeared and reformed the yellow color that we observed in the initial stages. This is because upon addition of H+, phenoxide anion converts back into phenol. Therefore, you break the complex that is formed between Fe3+ and phenoxide anion, because phenoxide anion will no longer be there. Instead, it will form phenol. So therefore, due to the absence of Fe3+ and phenoxide anion complex, we do not observe the violet color. Instead, we have the yellow color that we observed in the previous Fe3+ neutral solution. In summary, in this part of our experiment, we initially started with observing the properties of ferric chloride salt. We observed that the ferric chloride salt is an acidic salt. After checking the pH of ferric chloride solution that we have, we decided we need to obtain a neutral ferric chloride solution. And we prepared a neutral ferric chloride solution by adding ammonium hydroxide or dilute ammonia until we obtain a brown color precipitate. Afterwards, we filtered the suspension and we obtained our brown color precipitate ferric hydroxide on the filter paper, and as the filtrate, we obtained our ferric chloride neutral solution. We have our ferric chloride neutral solution as our filtrate. Afterwards, we took a small portion of ferric chloride neutral solution and reacted it with phenol. When we reacted it with phenol, we observe when ferric chloride neutral solution reacts with phenol, it produces a violet color solution. This is due to Fe3+ ions forming a complex with phenoxide anions. Upon addition of hydrochloric acid to the purple color solution we had, we were able to decolorize the purple color and obtain the color of ferric chloride that we observed earlier. This is because when H+ is added to the medium, phenoxide ion reacts with the H+ and forms phenol again. Therefore, the complex ion that gave us the violet color solution will break, and therefore we will not observe that violet color. So the purple color or the violet color solution was due to a complex formation between Fe3+ and phenoxide anion, and when H+ is introduced, phenoxide anion will turn into phenol, thereby breaking the complex. This is all for the final part of our experiment. Now let's move on to important theory parts and questions revolving around this practical.
GCE Advanced Level Chemistry Practical Series Experiment number 26, Properties of Phenols. Students, in the beginning of this practical, we had a look at the theory parts revolving around this practical or properties of phenol. And then we went into the lab and conducted the experiment, and right now we are going to be discussing some questions revolving around properties of phenols. Let's take a look at the question number 1. Explain how organic compounds given below can be identified separately. So they're asking us to separately identify the organic compounds that are given below. Now, first one we have phenol and benzyl alcohol. Phenol and benzyl alcohol. And then we have propanol and phenol and benzoic acid and phenol. So let's take a look at how we can separately identify these compounds. The first one is phenol and benzyl alcohol. So when it comes to phenol, you know the OH group is directly connected to an aromatic or benzene ring. However, when it comes to benzyl alcohol, the OH group is not directly connected to the benzene ring. So this is merely a primary alcohol. This is a phenol which is having different properties compared to alcohols. So we know a few properties of phenols. Phenols readily react with things like bromine water. They do not show reactions where they form esters when reacted with carboxylic acids. Phenols can't be oxidized like primary alcohols. So these type of properties can be used to identify these two compounds separately. So let's list down a few. Now, if you take bromine water, what is the reaction that is going to happen with phenol and what is the reaction that is going to happen with benzyl alcohol? When it comes to phenol, we know they are going to produce 2,4,6 tribromophenol. 2,4,6 tribromophenol, which is going to look like this. So this is carbon number 1, this is 2, this is 3, 4, 5 and 6. You can see at the 2nd, 4th and the 6th positions bromine is substituted. So therefore we call this 2,4,6 tribromophenol. This is going to be a white color precipitate. So when you're adding bromine water to phenol, you're going to see a white color precipitate form. That is one of the observations. The other main observation is the brown color of bromine will be decolorized. So you can write brown color will be decolorized. What will happen when we do the same or when we add the same reagent, bromine water, to benzyl alcohol? Alcohols doesn't specifically show a reaction with bromine water. So there's going to be no reaction. There's going to be no change. We are not going to have any change. As you can see, when it comes to phenol and benzyl alcohol, if you are reacting both of these compounds with bromine water, we are going to see the bromine water's color getting decolorized in the presence of phenol and formation of a white color precipitate, as I mentioned earlier. However, when the same bromine water is reacted with benzyl alcohol, you do not see any observation, you do not see any change. The bromine water's color will not be decolorized, as well as there won't be any precipitate formed. So therefore, we can use bromine water to separately identify these two compounds. Phenol and benzyl alcohol can be separately identified with the use of bromine water. Now let's move on to another test that can be used. let's move on to another test that can be used. As you know, as I mentioned earlier also, primary alcohols can be oxidized. Secondary alcohols also can be oxidized. However, can phenols be oxidized? No. So therefore, we can use an oxidizing agent and convert this primary alcohol into a carboxylic acid. So if you use acidified potassium permanganate, do you see any observation when it comes to phenol? We do not see any observation when it comes to phenol. However, if you are reacting acidified potassium permanganate with benzyl alcohol, which is a primary alcohol, primary alcohols can get oxidized into aldehydes and then into carboxylic acids. So let's move on to the observations here. When it comes to phenols reacting with acidified potassium permanganate, you do not see any change. So we can write no change. However, when you're reacting acidified potassium permanganate with benzyl alcohol, we are going to see the purple color. Purple color of potassium permanganate will turn colorless. Purple color will turn colorless. And the product that is going to be formed is going to be this. So benzyl alcohol will turn into benzoic acid. And is benzoic acid soluble in water? No. So therefore, we are going to see the formation of a white color precipitate. We are going to see the formation of a white color precipitate as well. So these are the two observations that you will come across when you are reacting acidified potassium permanganate with phenol and with benzyl alcohol. So a similar observation can be made when you take a different oxidizing agent, which is acidified potassium dichromate. You can use acidified potassium dichromate for this reaction as well. So when you're using acidified potassium dichromate, if we quickly have a look at it, if you're using acidified potassium dichromate, you will observe when it comes to phenol, there won't be any change. When it comes to phenols, there won't be any change. However, there will be a change when it comes to benzyl alcohol. So we are going to be using acidified potassium dichromate. So the dichromate ions are normally orange in color. So we have orange color solution here. What happens when it comes to reacting acidified potassium dichromate with phenol? No change. Why is there no change? As phenols don't get oxidized in the presence of oxidizing agents such as acidified potassium dichromate or acidified potassium permanganate. And then if you take benzyl alcohol, you will see similar observations to what you saw earlier. Since the oxidizing agent is going to undergo a reduction, you are going to see a color change. Acidified potassium dichromate or dichromate ion, Cr2O7 minus ion, gets converted into Cr3 plus ions. Cr2O7 minus is going to be orange in color. and the resultant chromium 3 plus aqueous solution will appear green in color. So you will see a orange to green color change. Apart from that, the same white precipitate is going to be observed as benzyl alcohol get oxidized. As benzyl alcohol get oxidized, you will be forming benzoic acid, which is going to precipitate as a white color precipitate, as it is not soluble in water. So these are the observations you will be noticing when you are reacting acidified potassium dichromate with phenol and benzyl alcohol. Right. Now let's move on to the next way in which we can identify these two. So let's move on to a fresh page. Now students, apart from these two methods, one we used bromine water, second time around we used oxidizing agents like potassium permanganate and potassium dichromate in acidic medium. We can also use neutral FeCl3. So let's have a look at the reaction that takes place there. So we have phenol here, and we are trying to separately identify phenol and benzyl alcohol. Now, if you use neutral FeCl3, now in the theory parts we studied, neutral FeCl3 is going to give us a violet color when the OH group is directly connected to the benzene ring, or basically when phenols are present, or when carboxylic acids are present. So if you observe here, when we are adding neutral FeCl3, only one of these compounds are a phenol, or the OH group is directly connected to a benzene ring in only this compound, which is our phenol. The other one is a primary alcohol. So primary alcohols do not show a reaction between neutral FeCl3 and primary alcohol. So therefore, you will not see a violet color when it comes to the primary alcohol. You will observe a violet color solution being formed when it comes to FeCl3, neutral FeCl3 reacting with phenol. When it comes to the primary alcohol that we have here, which is benzyl alcohol, you will observe no change. Now we can take this a step further, which is if you add dilute HCl, you are going to see this violet color disappearing. As we discussed in the theory parts, the violet color is going to be observed because the phenoxide anion is capable of forming a complex with Fe3+. So as we add dilute HCl, phenoxide anion will again convert into phenol. So at that point, since the complex is going to be not present anymore in the medium, you're going to see the violet color disappearing as we add HCl to the medium. Apart from that, we can use another test, which is when you're talking about phenol and a primary alcohol, we can add aqueous sodium hydroxide and see which one of these compounds actually react with aqueous sodium hydroxide. As you know, students, when it comes to alcohols are not that acidic compared to phenol. So alcohols are capable of reacting with metallic sodium. Phenols are capable of reacting with metallic sodium and sodium hydroxide. And there's another acidic compound that we come across, which is carboxylic acids. Carboxylic acids are acidic enough to react with metallic sodium, sodium hydroxide, and also sodium carbonate or sodium bicarbonate. Phenols are not strong enough to react with sodium carbonate or sodium bicarbonate. However, carboxylic acids are. Now at this point, we are focusing on the reaction with sodium hydroxide. We saw, as we discussed just now, we know that phenols are capable of reacting with sodium hydroxide. However, alcohols are not. So if you add a small amount of sodium hydroxide into the medium, you will see phenols dissolve in the sodium hydroxide. Therefore, there won't be any layer separation. Normally, phenols are not very water soluble. So normally when you are adding phenol and water together, you are going to see two layers being formed. However, when you are adding an aqueous solution of sodium hydroxide, although the medium here of sodium hydroxide is aqueous, since phenol react with the aqueous medium's sodium hydroxide and forms phenoxide ions which are soluble in water, you will not see the formation of two layers. You will see a single layer, or we can say no layer separation. There won't be any layer separation. Apart from that, you're going to see when it comes to this reaction, you're going to form phenoxide anion, which is going to be soluble in water. However, when it comes to this alcohol, you can see there's a large aromatic group. Alcohols with these types of large benzene rings are not going to be soluble in water. At the same time, alcohols do not react with sodium hydroxide. So therefore, you will see there are two layers being formed. Two layers will be observed, and no reaction between sodium hydroxide and the alcohol. So that is another test that we can use. Apart from that, we can use litmus paper. Right, so when it comes to litmus paper, phenols are capable of turning blue litmus paper red. Phenols are acidic enough to turn blue litmus paper red. However, we are going to observe that alcohols are not acidic enough to no change observed here. When you're trying to test out the acidity of an alcohol with the use of litmus paper, you will not observe blue litmus paper turning into red. However, phenols will turn blue litmus paper to a red color. And we do have other methods as well. Let's look at all of these methods so that you have a clear and a complete idea of what main methods are there to identify between these two. Apart from the experiments that we have mentioned over here, we can use reactions that are mainly seen in alcohols to identify between phenols and alcohols. Reactions such as esterification reactions. If you take carboxylic acid, we'll take CH3, COOH. And if you react this in the presence of concentrated sulfuric acid, and heat it, phenols are not going to show a reaction. However, benzyl alcohols, which is a primary alcohol, will show a reaction. Over here, we are going to see no change. But what about primary alcohol? Primary alcohols for sure will show a reaction and you will see the formation of an ester. Now, how do we identify the presence of an ester? Through the smell. Esters normally have a characteristic smell. So as an ester gets formed, you can actually sense or observe this characteristic smell due to the formation of the ester. So to properly observe the smell, we normally add a small amount of sodium bicarbonate to neutralize the excess acid in the product so that we can obtain the ester without any impurities of the acid. So we add sodium bicarbonate to neutralize the excess acid that is there. So normally we'll see when esters are being formed, adding sulfuric acid along with the carboxylic acid here is the first step. As a second step, we can add sodium bicarbonate to the product that is formed. So then we can very clearly observe the smell that is released due to the formation of the ester. Now, there are reactions that are specific to phenols as well. For example, when you react benzene diazonium chloride with phenol in the presence of an alkaline medium, we know that we are going to get an azo dye. So that also can be used here to separately identify these two. So if you take benzene diazonium chloride and react this with the other two compounds in an alkaline medium while maintaining a temperature of 0 to 5 degrees Celsius, you're going to see phenols will react to form an orange color azo dye. However, when it comes to primary alcohols, you will not see such azo dyes being formed. So therefore, there's going to be no change here. You won't see any color change over here, but you can see an orange color azo dye being formed here. So the formula of the azo dye that is being formed here would be this. Now students, we know a few ways in which we actually can identify these two compounds separately. We discussed about 5 to 6 methods which actually can be used to identify a phenol from an alcohol. Now let's move on to the next part of this question. Now students, we have the second part of this question. Again, we are going to be asked how to identify between propanol and phenol. Propanol is a primary alcohol and we have phenol which are going to have different properties compared to alcohols. So therefore, we can actually use the same tests that we mentioned in the previous question. So instead of going through them again, looking at the products that are being formed, let's list down the main tests that can be used to identify between a primary alcohol such as this one and a phenol. First test that we can use is bromine water. We saw no change here and when it comes to phenol, we are going to observe a white color precipitate being formed. So we see no change. Bromine water will be decolorized. And a white precipitate and a white PPT or precipitate will be formed. And then we can use another test to identify these two, which is neutral FeCl3. When it comes to primary alcohol, we will not observe any change. But when it comes to phenol, we can see violet color solution being formed. So this is number 2. Number 3, we can use an oxidizing agent. So I'm not going to write the actual color changes, but we can list down the oxidizing agents. We can use acidified potassium permanganate or acidified dichromate. Both of them are capable of oxidizing alcohols. So they will be producing a carboxylic acid this carboxylic acid doesn't have a benzene ring attached to it, so you will not be observing this as a white color precipitate because this has somewhat of a higher solubility in water compared to a benzoic acid. So you will not be observing this formed as a precipitate. However, you will observe the color of the oxidizing agent changing when it comes to potassium permanganate from purple to colorless. When it comes to potassium dichromate, you'll be seeing the color change from orange to green. So we will write the color changes from purple to colorless. When it comes to potassium dichromate, we are going to observe from orange to green. When it comes to phenol, there's going to be no change. Right. So this is the third experiment we can use to identify these two compounds separately. What are the other ones that we used? We used aqueous sodium hydroxide. We can use aqueous sodium hydroxide. However, in this particular test, we can't use aqueous sodium hydroxide because when you are using aqueous sodium hydroxide to separately identify a primary alcohol and phenol, the primary alcohol, if it is already soluble in water, you will not necessarily be able to identify any, or you will not be able to observe any change. As phenols dissolve in sodium hydroxide, they will form no layer separation. But an alcohol like propanol is small enough to dissolve well in water. So if you add aqueous sodium hydroxide, it will dissolve in aqueous sodium hydroxide because the medium is aqueous. Although there is no reaction between sodium hydroxide and the alcohol, alcohol will dissolve in water because these types of small chain alcohols or alcohol with smaller carbon chains will dissolve easily in water. So therefore, we can't use sodium hydroxide. We can't use sodium hydroxide to identify between the two compounds that are given here. But we can use other tests such as litmus. The fourth test would be the use of litmus paper. So when it comes to propanol, propanol will give us no change, but phenol will convert blue litmus paper into a red color because phenol is acidic. What other tests can be used? Like I mentioned earlier, there are tests that are characteristics to alcohols, such as formation of esters. So we can actually use that by using, we have an alcohol here, so we can employ a carboxylic acid like acetic acid along with concentrated sulfuric acid, and you can heat the mixture. So this is normally the part 1. Part 2 is where you add sodium bicarbonate to the product that is formed. A small amount of sodium bicarbonate solution can be added to the product that is formed to neutralize the excess acid. Right, so when it comes to reacting, we have here propanol and acetic acid. You're going to form an ester. If you want to write the equation for the ester, we can. So this ester that is being formed is going to have a characteristic smell. The characteristic smell of esters will make us understand that propanol reacts with acetic acid in the presence of concentrated sulfuric acid to form an ester. However, you will not be observing a smell or ester related smell when it comes to phenol. So therefore, there's going to be no change here. There won't be a change when it comes to a phenol reacted with a carboxylic acid in the presence of sulfuric acid and heat. Now, like I mentioned earlier also, when it comes to alcohols, we have characteristic reactions, as well as when it comes to phenols, there are reactions that are specific to that. And we discussed about this earlier, which is the reaction between phenol and benzene diazonium chloride in the presence of sodium hydroxide. And what is the temperature that we are going to employ for this particular reaction? 0 degrees to 5 degrees Celsius. 0 to 5 degrees Celsius temperature will be used. So what are the products that are going to be formed here? When it comes to propanol, do you see any products being formed? No. So there won't be any change here, no change. What about when you are reacting phenol? We are going to be observing the formation of an orange color azo dye. Orange color azo dye will be formed. Which is going to be having this formula. So this indicates that we can use reactions that are specific to phenol to separately identify phenol from other compounds, such as primary alcohols that we saw in the first part and the second part of this question. Right, students. So now let's move on to the third part. Actually, when it comes to the second part, we observed six different methods. 6 different methods that can be that we can use to separately identify phenols from primary
alcohol that we have here, which is propanol. While keeping that in mind, let's move on to our next question. In this next part, they're asking us to separately identify benzoic acid and phenol. Benzoic acid and phenol. So some of the tests that we used in the previous part can be used here as well. We'll be using few of the tests that we saw in the previous two parts here as well, such as addition of bromine water. If you add bromine water, you are going to observe no change here, but you will be observing decolorization of the brown color. Of bromine water. That is point number one. Second point would be formation of a white color precipitate. Formation of white precipitate. Now students, another very interesting test that we can use to identify between a benzoic acid and phenol is the use of neutral FeCl3. So this can be done in two steps. Step number one, addition of neutral FeCl3. That's step number one. What are we going to observe when it comes to benzoic acid? Benzoic acid is going to form a violet solution. We know phenol also forms a violet solution. So you may ask, if that is the case, why do we use this? You don't see any difference here. Actually, the main observation will come through when we do the second part of this test, which is the addition of dilute HCl. So when you add dilute HCl, again, violet color will be decolorized. We can write that is one observation. Decolorize violet color. And apart from that, when it comes to benzoic acid, since the benzoic acid is going to be reformed in the presence of a strong acid like HCl, you will not have the benzoate anion, which is the soluble form of benzoic acid or water soluble form of the benzoic acid. So when the benzoate anion is present in water, it is water soluble. However, as H plus comes into the medium due to addition of a strong acid like HCl, H plus will react with the benzoate anion in the medium and will form benzoic acid again. So benzoic acid is not water soluble. So you will see benzoic acid will be precipitating out as a white color precipitate. Since benzoic acid is not water soluble, you can see the formation of a white color precipitate upon addition of dilute HCl. And what happens when it comes to phenol? When you add dilute HCl, you are going to only see one observation, that is decolorization. Decolorization of violet color. So these are the observations when it comes to
the reaction with neutral FeCl3. Apart from that, we can use other reactions as well. You know, in the beginning of this discussion, I mentioned that sodium carbonate and sodium bicarbonate, sodium carbonate and sodium bicarbonate can react with only carboxylic acids. Only carboxylic acids can react with sodium carbonate and sodium bicarbonate. So when you have benzoic acid, they will react with the benzoic acid and will form gas bubbles, or CO2 will be released. So you can say formation of bubbles, or bubble formation. Or we will say effervescence will be observed. Effervescence will be observed. However, when it comes to phenols, since phenols are not acidic enough to react with sodium carbonate or sodium bicarbonate, you will see no change. You will see no change there. So, apart from these three tests, we can use other tests that are very specific to phenols and carboxylic acids. So there are some reactions that are very specific to acids or carboxylic acids. For example, you know, when it comes to reacting a carboxylic acid with an alcohol, we can form an ester. So we have a carboxylic acid here. So we can use an alcohol and convert this carboxylic acid into an ester. So the fourth step can be the use of an alcohol such as ethanol in the presence of concentrated sulfuric acid and heat. You will be observing the formation of an ester. So we have benzoic acid here. It will form the following ester. Although you will not necessarily observe the structure, this is not observation, this is for your knowledge. You can't observe the structure of the ester that is being formed when the reaction is happening. However, you can observe the smell, or you can sense the smell that is released when an ester is formed, because esters, when they're getting formed, they will release a very characteristic smell will be there. So there will be a very characteristic smell for esters that is going to be observed when you are reacting a carboxylic acid and an alcohol together while forming an ester. However, when you are trying to form an ester with the use of an alcohol and a phenol, you will see no change. So we can use the formation of an ester to identify these two compounds separately. Apart from that, now this particular test, the fourth test that we used, was to identify the carboxylic acid mainly. There are reactions that are very specific to phenols. I have mentioned this 2 times earlier as well, which is the use of benzene disonium chloride to form an SO dye. So we can use benzene disonium chloride along with sodium hydroxide, employing 0 to 5 degrees Celsius temperature. You can form, when it comes to carboxylic acids, there will be no change. However, when it comes to phenol, you are going to observe the formation of an orange color precipitate or an SO dye, which is having this formula. This test can be used to identify benzoic acid and phenol separately. Now students, let's move on to our next question. Now let's take a look at the second question. Phenols react with the following. Phenols react with the following. So we have a few compounds that are given here. We have a diazonium salt here. We have nitric acid. We have HBr, and we have a benzene that is substituted with 2 nitro groups. So we know very well when it comes to diazonium salts and nitric acid, phenols will show a reaction. But phenols will not show reaction with HBr or a nitro group substituted benzene. So therefore, the answer is very clear, which is A and B only. So the answer is going to be 1. However, let's take a look at the products that are formed when benzene reacts with compound A and B. When phenol reacts with compound A. So we have phenol here. It's not benzene, we are talking about phenol. So phenol, when reacted with a diazonium salt, we know that phenols and diazonium salts together can form azo dyes. So in this reaction, when these two compounds react together, they will form this azo dye, so this is the product that is going to be formed when the azo dye that is given here reacts with phenol. So azo dye that is given here, when it reacts with phenol, you are going to see the formation of an azo dye. It's going to have an orange color or color ranging from yellow to red, will be normally observed when it comes to azo dyes. Apart from that, they have given another reagent that will react with phenol, and that reagent is nitric acid. So nitric acid definitely does react with phenol. And they form 2 main products. They can form ortho-nitrophenol or para-nitrophenol. Ortho or para-nitrophenol, actually not O, ortho and para-nitrophenol will be formed. So as you can see, I didn't write a third product where nitro group is connected to this position. That is because both of them are basically the same, either when it's connected to the second carbon from here or the second carbon from the other end. When there are no other groups present, it's going to give us the same compound, which is ortho-nitrophenol. And we have para-nitrophenol also formed in this reaction. So students, that is the answer to this question. The question is
Phenol reacts with the following, mainly the diazonium salt and nitric acid. Mainly the diazonium salt and the nitric acid will react with phenols. So the answer is A and B are correct. In the next part, they ask us to arrange the compounds given in the increasing order of acidity. Now, phenols are acidic. We know that. And we know alcohols are not acidic, or they are showing some acidic properties, but they're not acidic enough to even react with sodium hydroxide. They are acidic enough, however, to react with metallic sodium. So now they are asking us to arrange these in the increasing order of their acidity. So we'll start with phenol because we are familiar with phenol. So phenols are acidic as they are capable of donating a proton and forming a phenoxide ion. And we discussed in the theory parts, phenoxide ions are more stable compared to phenols. This is due to the negative charge here is going to be distributed in the benzene ring, and there's no charge separation unlike in the resonance structures of phenol. We looked at all of that in the theory parts. So when it comes to phenoxide ion, it is more stable compared to phenol. So because of that, a proton can be donated. However, when there is an electron withdrawal group connected, such as this nitro group that we have here, these are referred to as electron withdrawing groups. There can be a resonance where the double bonds electrons are donated to the oxygen right here, and therefore a double bond that is found on a benzene ring will actually come and form a double bond between a carbon and the nitrogen that is present here. Now students, when it comes to paranitrophenol is going to be more acidic compared to just phenol. This is because, again, this is an electron withdrawing group that is connected to the phenol here, and it is capable of distributing the negative charge throughout the remainder of the compound and increasing the stability of the ion that is formed. Compared to the phenoxide ion, the ion that is formed has its negative charge distributed throughout the ion, making it more stable. And since nitro group is more of an electron withdrawing group, the electron density of oxygen is going to further decrease, making it easier to break the bond between oxygen and hydrogen and obtain the electrons pertaining to this bond to oxygen releasing the hydrogen. So therefore, paranitrophenol or nitrophenols in general, or paranitrophenol in general, are more acidic compared to phenol. And then we have phenol connected to an electron releasing group. So these electron releasing groups are actually capable of donating a lone pair of electrons into the benzene ring and increasing the benzene ring's electron density, and thereby increasing the electron density around oxygen as well, making it difficult for the oxygen-hydrogen bond to break. So at this point, the release of a hydrogen is going to be even more difficult because of that the acidity of such a compound is going to be less compared to phenol. And finally, we have the alcohol. It's a tertiary alcohol that we have here. However, although it's a tertiary alcohol, it is not going to be acidic enough, or it is not going to be significantly acidic to release H plus easily. So therefore, even this, you wouldn't be able to see a reaction with sodium hydroxide. Even if you take a tertiary alcohol like this, you will not necessarily observe a reaction with sodium hydroxide, so it is not going to be acidic enough to compare with the acidity of a phenol. So it is going to have the lowest acidity out of the compounds that is given here. So at this point, we can see the answer is C should be having the lowest acidity, and then we have, bear with me, then we have D. After that, we have phenol, which is B, and finally A. So the answer is going to be 3. Answer 3, or the option 3, is your answer to this question. Now, we can move on to the next question. So, when it comes to observing these type of questions, first of all, before we move on to the next question, we have to make sure that you understand how different groups attached to the benzene ring is going to affect the acidity of a phenol. Electron withdrawal groups, when attached to the benzene ring of a phenol, it is going to increase the acidity of that particular phenol. However, if you have an electron releasing group connected to a phenol, it is going to bring down the acidity of a phenol. With that, we can move on to the next question. Bromine water reacts with the following compounds through a substitution reaction. Bromine water reacts with the following compounds through a substitution reaction. I think a key important point here is the substitution. Now, let's take a look at the compounds that they have given here. They have given phenol. Does bromine water react with phenol? For sure. Bromine water and phenol react readily, producing a white color precipitate, which is 2,4,6-tribromophenol. And while this reaction is happening, the bromine water will be decolorized. Does bromine water show a reaction with benzene? Not at all. You can't react benzene and bromine water at room temperature. You need other special conditions to attach bromine to a benzene ring. What about styrene? Styrene has a double bond. As we know, when it comes to alkenes readily react with bromine water as well. And then we have aniline. Aniline, just like phenols, show a fast reaction with bromine, producing 2,4,6-tribromoaniline, which is a white color precipitate. And just like in phenols, aniline will also decolorize bromine water while the reaction is happening. So let's take a look at these three things that we learned about just now. So we have phenols, we have aniline, and we have styrene. Right, so we will draw a small table here, so it will be easier for us to compare the changes that are taking place. Now, phenol has this structure. Aniline will have the following structure, and styrene has this structure. You can see styrene has a double bond. So when bromine water is added to each of these, what are the products that are formed? So you're going to observe over here, we form 2,4,6 tribromophenol, and here we form 2,4,6 tribromoaniline, and when it comes to this compound that we have here, styrene, we will observe the double bond will break and bromine will attach across the double bond to the carbons. So we can now observe the main changes that are happening. Now students, it's not just a matter of whether a reaction is observed between these compounds and bromine. The question doesn't ask which compounds does bromine react with. They want to see which compounds that bromine reacts via a substitution reaction. So let's observe the types of reactions that are happening here. We'll write it down in a different color. When it comes to reaction with phenol, it is an electrophilic substitution. An electrophilic substitution reaction. When it comes to aniline, also we will see it is also going to be an electrophilic substitution reaction. However, when it comes to the reaction with styrene, it is going to be an electrophilic addition reaction. It's going to be an electrophilic addition reaction. So therefore, we can't take styrene's reaction with bromine as an answer to this question. However, other two, phenol and aniline, can be considered as answers to this question. So if you move back into the question, you can see they are asking for only substitution reactions. So therefore, phenol and aniline will be the correct answers. Styrene and benzene will not be considered as correct answers. So the answer is D and A only, which is the fourth answer. Answer is D and A only. Now we move on to the next question. In this next question, they're asking us about structure of D. They say the structure of D is given. So this is D. Explain how the compound D can be formed with the use of 2-naphthol and benzene as the only organic compounds. Now students, those of you who have studied phenols or gone through the theory parts of phenol, we had a look at 2-naphthol and reaction with diazonium salt. So we can observe here the presence of 2-naphthol. So this is our 2-naphthol. You have the OH group connected here. So this is referred to as 2-naphthol or beta-naphthol. We can identify the presence of the same compound over here. And this second section that we see should be formed through benzene, because we are only given beta-naphthol and benzene to produce this compound D. This is an azo dye. So we know when it comes to forming an azo dye, we need to have a diazonium salt reacting with, in this case, beta-naphthol or phenol. So we have already been given beta-naphthol. Now we need to figure out a way to form a diazonium salt starting with benzene. So let's move on to that. So we can write formation of diazonium salt. So we can start with benzene. And if you react benzene with concentrated H2SO4 and concentrated nitric acid, you are going to observe the formation of nitrobenzene. You will see you are going to form nitrobenzene. And then nitrobenzene can be converted to aniline. How do we do that? We can take tin and concentrated HCl. In the presence of tin and concentrated HCl, and if we use a setup heat under reflux, you will obtain aniline. Now we are almost there. So how do we convert aniline into a diazonium salt? So aniline can be converted into a diazonium salt by taking sodium nitrite and reacting it with HCl. Sodium nitrite and HCl together can form nitrous acid, and this reaction actually should be conducted at temperatures between 0 to 5 degrees Celsius. This will result in the formation of benzene diazonium salt. This will result in the formation of benzene diazonium salt. So benzene diazonium salt, when reacted, so they are asking us to show, explain how the compound D can be formed. So after the formation of benzene diazonium salt in the following manner, we can react this benzene diazonium salt with beta-naphthol or 2-naphthol. So we have our benzene diazonium salt here, and we have our beta-naphthol here, or 2-naphthol. When you react these two in the presence of sodium hydroxide, and the temperature also should be maintained between 0 degrees to 5 degrees Celsius, you will be obtaining this compound, which is going to be the compound D. They have given you compound D. Normally, when it comes to phenol, we saw the para position is where the diazonium salt will attach to the phenol. However, in this beta-naphthol, you can see the para position is blocked. So therefore, ortho position will be used instead of the para position. So this is your compound D. So you can form this compound D when you react your benzene diazonium salt that is produced with beta-naphthol in the presence of sodium hydroxide, employing a temperature between 0 to 5 degrees Celsius. Right, so again, just to recap what we learned, we identify the presence of 2-naphthol or beta-naphthol here, and then we identified what we have formed here is an azodie. Azodies have this characteristic feature where you have this structure across the nitrogens that are connected with double bond. You can have two benzene rings or aromatic groups connected to it. Over here also we observe the same structure. So this is an azodie. So an azodie can be formed when phenol or compounds like beta-naphthol or 2-naphthol is reacted with a diazonium salt. So after identifying the diazonium salt needs to be formed, we looked at how benzene can be converted into a diazonium salt. We see the conversion of benzene to a diazonium salt here. And then after the diazonium salt is formed, we will be reacting the diazonium salt with beta-naphthol or 2-naphthol to produce the compound D. Now this is going to be produced as a red color azodie. It's a red color azodie. Now let's move on to the next question. What are the products when ammoniacal silver nitrate is reacted with propanol? So students, this is a part of the same question we saw earlier, 4b. So we have ammoniacal silver nitrate. Ammoniacal silver nitrate is basically your Tollens reagent. So Tollens reagent, when it is reacted with propanol, they're asking you what the products are. So we will quickly take a look at this as well. CH3, CH2, C double bonded oxygen, and hydrogen is the structure of propanal, right? So this is an aldehyde, and this is going to react with ammoniacal silver nitrate. So ammoniacal silver nitrate has the following formula. So silver ions are forming 2 coordinate bonds with ammonia ligands, forming this. Complex ion. And since this is an alkaline medium, there will be hydroxide ions in the medium and nitrate ions in the medium. So we can write it like this. Even if you write with a nitrate ion, that is also correct. This will convert into silver solid. Silver ions get reduced to form silver solid. So this is the reason when you are carrying out a reaction with the use of Tollens reagent, if the second reagent is undergoing oxidation, the silver ions will definitely undergo a reduction, forming silver solid. So when the silver solid is formed, one of the observations you can see is, if you are doing this experiment in a test tube or a boiling tube, the silver solid that is formed will be deposited in the interior wall of the test tube or the boiling tube. So the internal or interior wall of the test tube or the boiling tube are going to be covered with silver solid. So when a glass has one side of the glass covered with silver, it is going to appear as a mirror. So we call this the silver mirror test. So as silver ions get reduced to form silver solid, you can observe a very nice observation, which is the formation of a silver mirror. So if this is the test tube over here will turn into a mirror where you can see yourself as well. So this is a test that is normally done to identify the presence of an aldehyde. So propanal will reduce the silver plus ions into silver solid, while propanal get oxidized to form propanoic acid. However, since this is happening in alkaline medium, propanoic acid will be formed in the form of propanoate, which is the anion. As soon as propanoic acid is formed, in the alkaline medium it will react, and what you are going to obtain is propanoate. So keep this in mind. These are the two main products that you're going to observe when carrying out this reaction. When carrying out this reaction, a silver mirror, formation of silver solid, is observed through the silver mirror, and the second product that is formed is going to be propanoate anion. Now we move on to the fifth question. In the fifth question, they're asking us, give two tests that can be used to separately identify the two compounds given below. We have salicylic acid here, and we have a benzene group connected to a phenol group, and over here we have NH2Cl and a CH3 connected to the benzene. Now students, when it comes to a compound like this, I know that a lot of the students get confused as to what this group is. So to clarify that, let's quickly move on to aniline. So if you have aniline, reacting with an acid, what is the observation that you come across, or what product would be formed? So the product that is formed will be referred to as phenylammonium chloride, which is this. So how does this happen? Since there's a lone pair of electrons, on nitrogen when it comes to aniline, when the HCl is introduced into the medium, the H plus concentration will go up, and this lone pair can be donated to one of the H pluses in the medium. As we know, aniline is capable of acting as a base. Why is it acting as a base? Because it is capable of donating a lone pair of electrons to a proton and accept a proton. So the ability aniline has to donate a lone pair of electrons and accept H pluses is going to be the reason why we categorize aniline as a base. Aniline shows why aniline has basic properties because it can accept protons. So when it accepts protons, you can see the formation of phenylammonium ion, and then when chloride ions are joined to it, we form phenylammonium chloride. Now similarly, when you have a compound like this, this also has a lone pair
of electrons on nitrogen. So if you react this also with HCl, you can see when the medium has H plus ions, a lone pair can be donated from nitrogen to the H plus ions to form this compound. So that is what we have here. So this is going to be positively charged at this point, right? You can see there's no lone pair of electrons on nitrogen, and a chlorine or chloride ion can actually get attracted to this positively charged ion and form this compound. So that is what we have in this question. So you have to understand how this is formed so that you don't have any hesitation when it comes to attempting a question like this, or feel like this is a compound that you have not come across before. We have the chloride ions here. Now they're asking you to give two tests to identify these two compounds separately. One of the tests is quite easy to conduct, right? We can see when it comes to this compound, if it is present, or if you are adding a solution such as silver chloride or silver nitrate or lead nitrate, due to the presence of the chloride ion, we can precipitate these chloride ions as silver chloride or lead chloride. So we can write down two tests like this. If you add dilute nitric acid and then add silver nitrate solution, you can see when it comes to salicylic acid, there's no reaction, or there's going to be no change. There won't be no change. But when it comes to this compound, we can see there is chloride ions in the medium, so it will form silver chloride, which is water insoluble, and it is going to be present as a white color precipitate. It is going to be formed as a white color precipitate. So that is one of the tests that we can use. Similarly, we can use another test where we add lead nitrate. So we'll have a look at that as well. If you take lead nitrate, before we add lead nitrate, we'll add a little bit of dilute nitric acid, and then we'll add lead nitrate. When it comes to addition of lead nitrate, there will be no change in salicylic acid. However, when it comes to the compound given above, you will be forming, since there is chloride ions in the medium, you will be forming lead chloride, again, which is a white color water insoluble precipitate. White color water insoluble solid, which is going to be produced as a white color precipitate. Now, are there any other ways in which you can identify these two separately? Yes, there are other ways. We will take a look at that as well. So when it comes to identifying two compounds, try to find out reactions that are very specific to the functional groups that are present in those compounds. So when you're taking a look at these two compounds, we can see there's a carboxylic acid group here. There is no carboxylic acid group here. When it comes to both the compounds, you have the OH group or phenolic group. So there are four. You will not be able to use reactions that are specific to phenol. However, since carboxylic acid is present over here and no carboxylic acid present over on the compound on the right hand side, we can actually use the presence of the carboxylic acid to identify these two compounds separately. So if you are trying to react these two compounds with something like alcohol in the presence of sulfuric acid, you will be able to observe the formation of an ester. So if you take CH3OH, you'll be forming an ester here. An ester will be formed, and you will be observing the characteristic smell of the ester. But when it comes to the second compound, there will be no change. You will not observe a characteristic smell of the ester here in the second compound. So if you are assuming that you can use potassium or sodium carbonate or sodium bicarbonate because there's carboxylic acid here and there's no carboxylic acid present over here, that would not be possible because, as you know, if you take even compounds like phenylammonium chloride, those are acidic salts. So what we have formed here is an acidic salt. They are capable of reacting with water and releasing H pluses. So therefore, reacting with sodium carbonate or sodium bicarbonate will not be an option to identify these two compounds separately. We'll take phenylammonium chloride as an example. So we know when it comes to adding sodium carbonate, you can see if you take phenylammonium chloride, if you take phenylammonium chloride, if this is reacted with sodium carbonate, this can release H plus. As you know, the phenylammonium ion is now holding on to an additional proton. In the presence of water, actually, this can release the H plus that is present on nitrogen. And due to the release of this H plus, you can form sodium plus ions, and carbonate will get converted into carbon dioxide and water. Apart from that, phenylammonium ions will be turning into phenylamine or aniline. And the chloride ions that were associated with the phenylammonium ion will combine with the sodium ions to form sodium chloride. So these are the products when you are reacting a phenylammonium chloride with sodium carbonate. So in the presence of the second compound that is given here, you can see the nitrogen here has donated its lone pair of electrons to accept a proton, and we have formed an ion which is capable of donating the additional proton that is attached to the nitrogen. So we call these acidic salts. So when we have such an acidic salt, if you are going to react it with sodium carbonate, you will see the formation of effervescence or formation of bubbles due to the reaction between phenylammonium chloride, or in this case we have an acidic salt. Due to the reaction between the acidic salt and the sodium carbonate reacts, you can see the carbonate comes into contact with the proton that this compound is capable of releasing and will form carbon dioxide and water. So the formation of bubbles will be observed. So therefore, you can't use sodium carbonate to identify or separately identify these two compounds, because you can see the carboxylic acid will definitely react with sodium carbonate, and the acidic salt that we have here on the right hand side is also capable of reacting with sodium carbonate. Now let's move on to our next question. Now next question is asking us about an organic compound called W. It's telling us about an organic compound called W. W is an organic compound that has the formula C9H8O2. W decolorizes bromine water and it reacts with sodium carbonate. Draw the possible structures for W. So it decolorizes bromine water. So you can see reactions. We'll say the reactions that W take part in. So W can react with bromine water. So what groups can actually react with bromine water? There are two groups that are normally known to us. We know carbon double bonds, carbon triple bonds can react with bromine water to produce a decolorization of bromine water. Apart from that, they do not necessarily mention bromine water is decolorized and a white color precipitate is formed. They don't mention the formation of a white color precipitate, but we do know of another compound that is capable of decolorizing bromine water. This is phenol, or you can even take aniline, right? So, or phenylamine. However, these are not options. Why aren't phenol and phenylamine options? Because in this question, they don't necessarily mention to us that a white color precipitate is formed, right? Because when it comes to both of these compounds, a white color precipitate is going to be formed. Then we'll write it as PPT, white color precipitate. So decolorization of bromine water does take place in both phenol and aniline. However, they don't talk to us about the formation of a white color precipitate. And when it comes to aniline, you can see the presence of a nitrogen atom. In this formula, there's no nitrogen. So definitely these two will not be options for us. These two are actually options for us. And then they ask us, or they tell us that this particular compound reacts with sodium carbonate, Na2CO3. Now, what compounds normally are identified by the reactions with sodium carbonate? It's normally carboxylic acids. We use carboxylic acids to identify, or we use sodium carbonate to identify the presence of a carboxylic acid. So over here, what we have is definitely a carboxylic acid, because they say it reacts with sodium carbonate, or it dissolves in aqueous sodium carbonate. So if you have an organic compound, especially organic compound that has this many carbon atoms, 9 carbon atoms, are not going to be very water soluble. So we know large chain carbon organic compounds are not going to be very water soluble. They say this particular W compound dissolves in sodium carbonate, which means there is a reaction between this compound and sodium carbonate. In an aqueous medium, most probably this compound will not dissolve.
it will form two layers given the number of carbon atoms in the compound. So it might form two layers. However, in the presence of sodium carbonate, they say it dissolves, which indicates that there is a reaction. They don't directly say there's a reaction between the two. You have to identify the fact that there is a reaction between W, or compound W, and sodium carbonate, which means we normally identify the presence of a carboxylic acid with the use of sodium carbonate. So we are talking about a carboxylic acid here. So we have a carboxylic acid group and a double or a triple bond. So if you observe here, the number of hydrogen, they say C9H8O2. Number of hydrogens are extremely low here. For the 9 carbon atoms, there's only 8 hydrogens, which could indicate the presence of a benzene ring, because for each carbon there's only 1 hydrogen. And then we should have a double bond because we are talking about decolorization of bromine water. And apart from that, there should be a carboxylic acid group. So we will write that also here. And now we will fill in the hydrogens to observe if the number of hydrogens is a match to our formula. So we have over here 6 carbon atoms and 3 other carbon atoms here. Altogether carbon number is 9. Carbon number is 9. And let's take a look at the hydrogen atoms. There'll be 1 here, 2, 3, 4, 5. So 5 hydrogen atoms are also there, and 6th hydrogen atom is present here, 7 and 8. So we have altogether 8 hydrogen atoms and 2 oxygen atoms. So the formula that they have given is observed in this compound as well. So therefore, we can be fairly certain that this is our compound. Now they're asking us for the possible structures. So let's take a look at the possible structures. So this is one structure. So as soon as you see this structure, you should think of the geometrical isomerism that you observe here. This is a double bond. There's no rotation between the double bond, and you can see the 2 priority groups are present on the same side. So therefore, this is a Z isomer. We are talking about the EZ isomerism, just like cis trans. You can see the priority groups are on the same side, so therefore we can call it a Z isomer. And then we move on to the E isomer of the same compound. So this is our E isomer. You can see the 2 priority groups are across the double bond on opposite sides, not on the same side. So this is your E isomer. And then we can move on to other structures as well. These are not the only structures that you have over here. We can also have this carboxylic acid group connected to one of the carbons over here. If you take a look at this situation where the carbon, this particular carbon contains the carboxylic acid group. However, we can shift it to this carbon over here. At this point, you're going to observe that there is no geometrical isomerism in this compound. You can see across the double bond, or one of the carbons that are forming the double bond has 2 similar groups. So therefore, you can't have cis trans isomerism there. Now, we can move on to few other possible structures. For example, if you take the group where there's a double bond over here and shift the carboxylic acid group to another position, we will have another isomer. We can continue to shift this into two other positions. Now keep in mind, students, if the carboxylic acid group is present here or here, these are ortho positions. So regardless of which ortho position you choose and shift it to, you are going to have the same compound. So regardless of whether you write the carboxylic acid group here or in this location, keep in mind you are having the same compound. So there's no point in writing another isomer where you have shifted the carboxylic acid group to this ortho position. So therefore, do not change the position of the carboxylic acid group into the next ortho position. It will be the same compound. Then you can shift it to a meta position and finally to a para position. So these are 6 different isomers that you can have when it comes to benzene. We have the 2 geometrical isomers here, and then we can shift the carboxylic acid group into one of the different carbons present in the alkyl group present here. And then after that you can keep on shifting the carboxylic acid groups in different positions of the benzene ring. So these are the main isomers that can be formed when it comes to the compound W. Now let's take a look at the 7th question. There are 2 chemical tests listed below. We can see the reaction with FeCl3 and reaction with HNO2, and they're asking us to use either one of these tests to identify the compound pairs that they have given over here separately. So when it comes to FeCl3, FeCl3 can be used to identify the presence of a phenolic group, or even with benzoic acid. You will see FeCl3 will react to form a violet color solution. So FeCl3 can be used to identify these 2 main groups. And then we have HNO2. So what do we use HNO2 for? It's not HNO3, this is nitrous acid. Can you remember when it comes to formation of diazonium salts, we use this reaction. We used this reaction. NH2 is reacted with sodium nitrite and HCl, and the degree Celsius temperature that we used was 0 to 5 degrees Celsius. So we used a temperature of 0 to 5 degrees Celsius, and we obtained our diazonium salt. So this reaction required sodium nitrite and HCl. So when sodium nitrite introduces nitrite ions and HCl introduces H plus ions, the acid that is formed is nitrous acid, HNO2. So instead of using sodium nitrite and HCl, you can actually use nitrous acid, we have the nitrous acid here. So nitrous acid can be used to convert aniline into the diazonium ion, diazonium chloride or benzene diazonium chloride. So instead of using sodium nitrite and HCl, we can use the nitrous acid to convert aniline into benzene diazonium ions. So at the same time, students, if by any chance you carry out the same reaction but without controlling the temperature, imagine you used HNO2 this time, but you didn't maintain the temperature between 0 to 5 degrees Celsius. At that point, what you are going to be forming is a phenol. Along with that, you will see evolution of nitrogen gas. Nitrogen gas will be formed and released. So you can see the formation of bubbles. So when the temperature is maintained while you are reacting aniline or any NH2 group, for that matter, now we know phenylamine is the only compound, or when it comes to NH2 group, directly connected to benzene ring. The diazonium salts that are formed are stable. However, to make sure that they don't decompose easily, we use a temperature of 0 to 5 degrees Celsius. At higher temperatures, the diazonium salt is not going to be stable, so therefore you will be forming a phenol and nitrogen gas. But if you use an aliphatic amine and try to react it with HNO2, what would you observe? Do you observe the formation of a diazonium salt? No. You will not be observing the form of a diazonium salt because aliphatic diazonium salts are really unstable. Instead, you will be observing the formation of an alcohol. And you will be observing the release of nitrogen gas as well. So when it comes to the reactions with HNO2, HNO2 is a good way of identifying the presence of a amine group. So let's move on to this question. So we have looked at what type of reactions FeCl3 will, or what type of compounds FeCl3 will help us identify, and what type of reactions or compounds that HNO2 will help us identify. Now we have acetic acid and benzoic acid. So if you quickly move on to that part, you can see here we have acetic acid and benzoic acid. If you quickly write them down, CH3COOH, and benzoic acid would be this. You can see the acid group, COOH group, is directly connected to benzene. So if you react this with neutral FeCl3, you can see the formation of purple color or violet solution over here. Violet solution can be observed when it comes to benzoic acid, but no change when it comes to this compound or acetic acid. When it comes to adding reaction with HNO2, nitrous acid, there's going to be no change. There's going to be no change here in carboxylic acid, which is acetic acid that we have here. And when it comes to benzoic acid also, there's going to be no change. So the very first substance, acetic acid and benzoic acid, can be identified with the use of one of the tests. So you can use the reaction of FeCl3 and can identify these two compounds separately. So A can be identified with the use of one of the tests that we see here. Now we move on to the second set of compounds, 4-aminophenol and 2-nitrophenol. We have the amine, or we have the phenol here. So 1, 2, 3, 4, 4-aminophenol and 2-nitrophenol. When it comes to these two compounds, both contain the OH or phenol group. So what happens if you use neutral FeCl3? What happens? Both will actually form a violet solution. Both will form. This will also form a violet solution. So can we use neutral FeCl3 to identify these two separately? Not really. You can't. What about dilute HNO2? Can we use HNO2? Actually, when it comes to HNO2, we can see there's an amine group here. So if you don't maintain a specific temperature like 0 to 5 degrees Celsius, if you employ a room temperature and add nitrous acid into this compound, you can convert this amine group into an OH group. So this will be formed along with nitrogen gas. So you can see the formation of bubbles. That is observation. So there is an observation, visible observation for you to identify that HNO2 does react with 4-aminophenol. But if you are observing the reaction with 2-nitrophenol, there's going to be no change. Does HNO2 react with the NO2 group in 2-nitrophenol? No. So therefore, there is no change there. So we can use HNO2 to separately identify these two compounds. So can we use one of the tests to identify these two compounds separately? Answer would be yes. So this is also an answer. Now let's move on to the next question. You can see over here we have two NH2 groups. So at this point, now we are going to be thinking about FeCl3. As you can see, FeCl3 reacts with the phenol groups. So the phenol OH groups in these two compounds are present. So therefore, both compounds will turn the FeCl3 into O. When you react both of these compounds with neutral FeCl3, we will see the formation of a violet color solution. However, then we have NH2 groups. When you're trying to identify the presence of an NH2 group, you can use nitrous acid. What does nitrous acid do? In the presence of an amine group, nitrous acid will convert the amine group to an OH group, releasing nitrogen. So therefore, students, when you are considering these two compounds, you can very clearly see both will release nitrogen. So therefore, even the second test cannot be used at room temperature to identify these two. So if you noticed it, I mentioned at room temperature you can't use HNO2 or nitrous acid to identify between these two compounds. What does that mean? If you employ lower temperatures, if you employ lower temperatures like 0 to 5 degrees Celsius, when you react HNO2 with this compound to aminophenol, you are going to observe the formation of a diazonium salt. And what happens over here? Over here, since the amine group is not directly connected to the benzene ring, the NH2 will not form a stable diazonium ion, because at this point NH2 group, amine group, is connected to a CH2 group. So it is not an aromatic amine. So therefore, you are going to have an OH group formed here. Along with it, nitrogen gas will be released. So if you maintain the temperature between 0 to 5 degrees Celsius and then add nitrous acid, you can identify between these two compounds. However, if you employ room temperature, you will not be able to identify between these two compounds. So because of that, we can say still HNO2 can be used to identify between these two compounds, because in the question they don't have any mention about the temperatures that you can use. They say reaction with nitrous acid. So this is a reaction with nitrous acid. So if you are employing lower temperatures like this, reaction with nitrous acid will allow us to separately identify the two compounds due to one forming the diazonium salt and one forming an alcohol releasing nitrogen gas. So C is also an answer. At this point, you should be having a clear idea that the answer to this question is 5, because you don't have a combination like A, B, and C are correct. So therefore, the answer should be 5. But we'll take a look at this part as well. You can see you have an NH2 group and a carboxylic acid group, but this carboxylic acid group is not directly connected to a benzene ring. So therefore, this carboxylic acid group does not answer to FeCl3. When it comes to nitrobenzoic acid, we'll quickly draw the structure. 2-nitrobenzoic acid, you can see the benzoic acid group will answer to FeCl3. We'll draw this as well. So if you use neutral FeCl3, you will see no change here. And when it comes to this particular compound, 2-nitrobenzoic acid, due to the presence of the benzoic acid group, you can see the formation of a violet solution. Now, if you move on to the reaction with HNO2 nitrous acid, you can see the amine group that is over here will react with the nitrous acid to form an OH group in the position of NH2. So you will form the following compound while releasing nitrogen gas. When it comes to the second compound, 2-nitrobenzoic acid, you can see the nitro group doesn't react with nitrous acid. Therefore, you will see no change. You will see no change. So therefore, students, you can use the two tests that are given in the question to identify between these two compounds as well. So because of that, the answer to this question that we have over here is any other combination of answers. Because we can see all four of these compounds can be separately identified with the use of these two tests. So therefore, the answer is going to be 5. Now, with that, students, we conclude experiment number 26, identification of properties of phenols. We discussed the theory parts revolving around phenols, and then we conducted the experiment, and finally, we even looked at quite a few questions revolving around phenol. I hope you have developed a good enough understanding about the properties of phenols so that you can apply this knowledge to answering questions at your exam. So I will see you again in the next experiment.